Yes. Okay. Is my screen visible? Okay, 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 fine. Uh, Thank you, Professor, for this introduction. Should I? Okay, I may on my camera. Okay, fine, fine, fine. So, let me. Yeah. Everybody, this is visible to you. My screen is visible to you. Okay, so the title of my talk is Co-dimension and Bifurcations in a Discrete Time Ecological Models. So basically, last 3-4 years, I'm working in discrete time ecological model. And first of all, I would like to share that what is the motivation behind the work on discrete time ecological models. So. So as we know that the predator-prey interaction is the most fundamental process in population dynamics and population with overlapping generation. Overlapping generation means this the best example is we human being. We human being, if we talk about our parents, our grandparents, and our children are living together in a home. So this is the overlapping generation. It means that for 2 or 3 generations living simultaneously. So population with overlapping generation, the birth process occurs continuously. So ordinary differential equations usually model the predator-prey interaction. But many other species have discrete non-overlapping generation. Non-overlapping generation means that they are there's a certain life cycle after maybe 6 months, maybe 1 year, and after 1 year there will be no more that species. So but many other species have discrete non-overlapping generation and their birth occurs in regular breeding seasons. So we can see that some kind of the mosquito. So when we talk about the winter, like the rainy season, so season of the mosquito, and after some we can say that 2-3 months the entire the population of the mosquito die out. So such as the monocorpic plants and the semmelperous animals. Semmelperous animals is a very famous kind of the fishes also, that is it is found out in Bay of Bengal. So their interaction are described by difference equation or formulated as discrete time mapping. So the discrete time model can exhibit a wide range of complex dynamics, including intermittency, chaos, period doubling oscillation, and periodic windows. So sometimes that when we define the situation of non-overlapping generation, we require difference equation or discrete time equation. And the dynamics of the discrete time model is we can claim that it is much better, much complex than the continuous time model. So in discrete time model, the two species system can exhibit local and global dynamics along with chaos. As we know, and we talk about the continuous system, in the two-dimensional model, we can exhibit only the limit cycle. For the essence of chaos, there should be a three-dimensional continuous model or more than three. But in discrete time model, the two species system can exhibit chaos also. So this is the beauty of the discrete time models. And so it is in discrete time model, the two species system can exhibit local and global dynamics along with chaos, which is not feasible in continuous time system. And when we talk about the discrete time population models, so this is I would like to discuss our oldest discrete time population model. The model of population dynamics have its importance in the last few decades, but we often think this is a new and emerging area of research, but it is not so. When we talk about Fibonacci sequence, I think every mathematician knows what is the Fibonacci sequence, and they can be considered the first population dynamics model. And what is the Fibonacci sequence? It is a lead with the number of rabbits counted each month, because it is a we can say that if I talk about the Fibonacci sequence, we know that the one and the let's say we take the 1 and then 1 and second is the 2 and the sum 1 and 2 is the 3 and 2 and 3 2 and 3 the sum is 5. So this is the Fibonacci sequence. So it is a difference equation and it is defined like this: xn plus 1 equal to xn plus xn minus 1 and equal to 1 to 3, where x0 and x1 equal to 1. So there is a population model with Fibonacci sequence and rabbits and Fibonacci numbers. And we consider a problem which was posed by the Leonardo di Pisano, so known as the Fibonacci, at the very beginning of 13th century. So if we think that the discrete time model is very the topic of the last 2 or 3 decades, it's not so. It is very old topics. And what is the problem? A young pair of rabbits, one of each sex, is placed on an island. A pair of rabbits do not breed until or unless they are 2 months old. And it means after 2 months old, they are able to reproduce. After they are 2 months old, each pair of rabbits produces another pair each month. And find a recurrence relation for the number of pair of rabbits on the island after n months, assuming that no rabbits ever die. This is the problem that is resembled with the Fibonacci numbers. And this is the diagram. We can say that ignore this figure 1 is I think that's a kind of a mistake. So here we can see in this diagram the young pair. There's a less than 2 months old. We can see here the 2 young pair and less than 2 months old to 1 month old, so only 1 pair you can see here. When the second month, only 2 months to 1 young pair, so young pair 1 and total 1 pair. But after 2 months, the old 2 months old rabbit produces 1 young pair. So after 3 months, reproducing pair 1 hai, and 1 is the young pair. So total pairs, how many total pairs? This is 2. And similarly 4 months, because there's a 2 months, every 2 months, every month they will reproduce 1 pair. So 2 pair, so here the 3 pair. This is the problem of the rabbits, which is resembled with the Fibonacci sequence, and it is a problem which is defined the recurrence relationship between the rabbits and their reproduction. And it is the first model ever considered as a discrete model. So what is the discretization process? We know that there are different kind of the maps. So logistic map, Ricker map, Bevelton-Holt map. So what is logistic map? So here the xn plus 1 equal to r xn 1 minus xn over k, where n equal to 0, 1, 2, and we can extend it. So here the r is the reproduction rate and k is the carrying capacity. We know that there are limited resources in the nature, so the maximum bound is the K, is the carrying capacity. So RM May proposed this model in 1976 to analyze a simple looking one-dimensional non-linear map that could have very complicated dynamics. And it dynamics, the single, we can see here that this single species population model, where the population at the n+1 generation is a population function of the population of the previous generation. So it's a very famous discrete map, the logistic map. And then in ecology, the interaction between distinct species cause conflict. This may be the conflict and the cooperation and consumption. So what we do in the logistic growth model, we can write like this: dx over dt equal to x t on the 1 minus xt, the simple continuous model. And when we discretize it, so logistic map, by using what we do here, by using the Euler method, we can discretize also. And there's a Bevelton-Holt map. What we do here, the r xn 1 minus xn, we make some changes here. The capital R equal to r plus 1 and capital L equal to kr upon r with substitution, and the Bevelton-Holt map. So these are some example of the discrete model. I'm going to skip this part and straight away then I come to the discrete dynamical system. So consider an n-dimensional discrete time system. This is the fxi k plus 1. So it means the k plus 1 generation depends on the function, is a function of the xk, where I equal to 1 to n, and nu, this is a function, this is nu equal to nu1, nu and the parameter independent of k, and xk are the x1, x2, xn are the variable, and fi indicate the mapping vector. So simply we can write any discrete dynamical system, likewise the continuous dynamical system. There's a very famous result when what we use in the discrete dynamical analysis, and what we have, the consider a discrete non-dynamical system with an equilibrium point E star and Jacobian metric J star possesses n eigenvalues. Because when we talk about the stability and instability, then the main thing, if we talk about the continuous model, in continuous model, the threshold value equal to 0. When your eigenvalue is less than 0, then the eigen less than 0 are the negative, then the system the system at this equilibrium point, or we can say the eigenvalues are negative, then the system at this equilibrium point is stable behavior, otherwise unstable. Here, when we talk about discrete nonlinear dynamical system, the threshold value equal to 1. So here we can say that E star is called a sink and is locally asymptotically stable if eigenvalues are less than 1. This is the basic difference between the continuous and the discrete dynamical system. E star is called a source and is unstable if lambda I greater than 1. If all the eigenvalue greater than 1, then it is called stable. Where then continuous system, all the eigenvalues are the greater than 0 or the positive, then there is a instability. So this is the difference. And E star called a saddle and it unstable if at least one eigenvalue is greater than 1. And E star is called non-hyperbolic if lambda I equal to 1. It means the lambda, if one of the eigenvalue equal to 1, this is the threshold value, then non-hyperbolicity in the picture. And this is the very important thing. As we talk about the continuous system, when the eigenvalue is 0, so we are interested in that eigenvalues, and we try to explore the bifurcation at this point. And here the E star is called the non-hyperbolic. Now I come to the co-dimension and different bifurcation. Okay, so there are, because my topic is co-dimension M bifurcation, meaning co-dimension M, it means if we talk about bifurcation in one to the picture or dynamics change, then it is called co-dimension 1 bifurcation. When we make changes in 2 parameters, then bifurcation comes, dynamics change, then it is called co-dimension 2 bifurcation. It means when we talk about co-dimension M bifurcation, it means we change in M parameters. Yani ki when we when we make changes in M parameter and bifurcation occur, this is called the codimension M bifurcation. So here I would like to discuss codimension 1 bifurcation. It means we make a change in one parameter and dynamics change. So first is the limit point, and we can say the fold bifurcation also. If one eigenvalue is 1 and modulus of other eigenvalue not equal to 1, then the fold bifurcation comes. Next is the period bifurcation, and it is called also flip bifurcation. If one eigenvalue is -1 and modulus of other eigenvalues not equal to 1, this is called the flip bifurcation. And another one is Nemack-Secker bifurcation. Nemack-Secker bifurcation is analogous to Hopf bifurcation in continuous dynamical system. We know that Hopf bifurcation, the most famous bifurcation in continuous systems. So here we say it Nemack-Secker. Nemack-Secker, if lambda, the modulus of the eigenvalue is equal to 1, where both eigenvalues are complex conjugate. So Nemack-Secker bifurcation occurs. Similarly, now codimension 2 bifurcation. It means we make changes in 2 parameters simultaneously. So first is the Bogdanov-Taken bifurcation. The map exhibits Bogdanov-Taken bifurcation if Jacobian matrix has both eigenvalues equal to 1 under some non-degeneracy condition. Non-degeneracy means it means when we talk about the when we talk about continuous system, then we refer the non-degeneracy condition with respect to 0, and here we claim with respect to 1. Next is the Chancellor bifurcation, or sometimes it is called generalized Nemack-Secker bifurcation. The map exhibits Chancellor bifurcation near the Nemack-Secker point. It means Nemack-Secker bifurcation is the codimension 1 bifurcation, and Chancellor is the codimension 2 bifurcation. It means when we have the Nemack-Secker bifurcation and we make changes in other parameter, and then the Chancellor bifurcation occurs. So the map exhibits Chancellor bifurcation near NS point at fixed point E2 star if the Jacobian matrix has complex eigenvalue with unit modulus and NS coefficient equal to 0. We calculate Nemack-Secker coefficient, there are some formula that we can calculate, which can determine the Nemack-Secker coefficient. And next is the generalized period doubling bifurcations. It means this bifurcation occurs when the codimension 1 bifurcation, period doubling bifurcation occurs. Then we explore the possibility of GPD. This bifurcation exists when the eigenvalue of Jacobian matrix are 1 and other eigenvalues not equal to 1. Then the period doubling coefficient BPD will be 0. Next is the resonance bifurcation. Resonance bifurcation is also codimension 1 bifurcation. Codimension 2 bifurcation, codimension 3 bifurcation, but it's a different kind of bifurcation. Resonance bifurcation signifies the existence of multiple stable high periodic cycle between prey and predator in the ecosystem. So it furnishes a variety of strategy for the long-term coexistence of the both species. And there are the different type of resonance bifurcation: 1:1, 1:2, 1:3, 1:4. And when we talk about 1:4, then ecologically the prey-predator species coexist up to the 4th order in the stable high periodic cycle. So here 1:1 resonance bifurcation, simple. If both values are 1, then the 1:1 resonance bifurcation. 1:2, if both eigenvalues -1. So occurrence of R2, sometimes we can call it 1:2 resonance bifurcation is R2. So occurrence of R2 bifurcation implies that discrete model may exhibit Nemack-Secker, pitchfork and heteroclinic bifurcation in the neighborhood of fixed point. Similarly, 1:3 resonance bifurcation. Here, complex eigenvalues are third root of unity. You can see here. So the 1:3 resonance bifurcation indicates that an invariant curve of period 3 is bifurcated from the fixed point. And similarly, when we talk about 1:4 resonance bifurcation, and sometimes it is called the R4, when the complex eigenvalues are the fourth root of unity. These are the main thing regarding the resonance bifurcation. It evolves around the properties of eigenvalue. So 1:4 resonance bifurcation demonstrate that both species coexist till order 4 in stable periodic cycle near some critical parametric values. So I take I'm taking example. I take a continuous time model, how this bifurcation occurs in the system. So I take a continuous time model. It is discussed by the L chain and F chain. This paper is published in Nonlinear Analysis Real World Application in 2010. So I take this model, and here the alpha is the intrinsic growth of prey, M is the prey refuge, D is the predator death rate, beta is the maximum value of per capita reduction rate of prey, 1/A is the half saturation constant, and C is the conversion rate. So this is my continuous time model. What we do first, we discrete model. So by using Euler forward scheme, I discretize this model, and now we can write this model in the form of a map. So here fxy equal to this one. So this is a mapping. So first we find out the fixed point. So the trivial fixed point is 0, 0. Semi-trivial fixed point, it means that when the predator is 0. So semi-trivial fixed point, if b greater than 1. Any positive fixed point is C star, where X star equal to this and Y star. So it is not explicit point. It is written in the implicit way. So finally, by using I can summarize the result based on the we can say that as we talk about the trace and the determinant of the eigen corresponding matrix or the Jacobian of in the continuous time model, same here with the Jacobian matrix with respect to discrete time model. So here I say that we can write it's a form of polynomial lambda p lambda equal to lambda square minus trace j star lambda plus determinant be characteristic polynomial, and because it has a two-dimensional model, so there's a two roots of that the polynomial, this characteristic equation. So these are the result here where that we apply and find the characteristic value, find the characteristic of the eigenvalue, and find and can claim and can predict about the stability and instability. So here the stability analysis star, the E star is stable if and only if 2 plus 2 1 minus 2x star. This is the condition. Saddle, by using this previous lemma, we summarize the result regarding stability analysis here. Saddle if this condition hold, and the E star is unstable if this condition hold. And next is the bifurcation analysis. In this topic, in this model, first we analyze when co-dimension 1 bifurcation. So when b equal to 1 and m equal to this one, O is a non-hyperbolic fixed point, as I discussed earlier. We are interested in non-hyperbolicity. It means when the lambda 1 eigenvalue is 1. The map 2 undergoes when the transcritical bifurcation, when b passes through 1 and m is not equal to this, and the flip bifurcation, and we get the flip by for this condition. Similarly, at semi-trivial equilibrium point, this condition that the result A for the trivial fixed point, semi-trivial fixed point, we explore the flip bifurcation and transcritical bifurcation. And at positive fixed point, the system exhibits flip bifurcation if this condition holds, and Nemack-Secker bifurcation if b equal to 1 minus 2 x star. That is the simple numerical simulation for this set of parameter when a equal to 3, c equal to 4, m equal to 0.4, beta equal to 2. And because we talk about the co-dimension 1 bifurcation, it means we make changes in one parameter only. So here the bifurcation occurs with respect to b. So we can see here this diagram 1, the flip bifurcation diagram with respect to b here. So that there is a this is a flip bifurcation. What is the meaning of flip bifurcation? Flip bifurcation, it means, or we can say the period doubling bifurcation. So here the trajectory starts and it's split into two trajectories, and after that it splits into two. So it's a 2 to the power n. So period is a cascading effect of the doubling. So this is called the period doubling also. And similarly, the diagram B, the Nemack-Secker bifurcation. What is Nemack-Secker? You can see here that this is the up single line show the limit cycle. After limit cycle, there is a closed invariant curve with intermittent quasi-periodic windows, and there's a chaotic windows, and we can see the closed invariant curve. So that's why it is called the Nemack-Secker bifurcation. So in this model, we show two kind of the core dimension 1 bifurcation, flip bifurcation and Nemack-Secker bifurcation. And further, we apply the chaos control. So what is the chaos control? Consider a control system, and here we apply the state feedback method. In state feedback method, we apply controller force UN, and UN is it's a kind of a linear term, V1 xn minus x star plus V2 y1 minus y star, and denotes the controller force, and V1 and V2 are the feedback gain. So we find the characteristic equation corresponding to this control system. These are the trace, this is a determinant, and now the condition for the marginal stability line, when the lambda is one eigenvalue is plus minus 1 and the determinant equal to 1, and for the stability, all eigenvalue lie in the triangular region. So we find the three marginal stability line, L1, L2, L3, and these are the condition for L1, L2, L3. When for the stability region, when we draw this region like this, you can see here they are the L1, L2, L3, and this is the common region. The region bounded by these three lines show the stability region where the system show stable always. So stability region for the control system, and this show as the system is stable. Excuse me. And if we draw a bifurcation diagram with respect to V2, so bifurcation diagram for control system at V1 equal to this and V2 in this range, and we apply the state feedback. So we can see here as for Nemack-Secker bifurcation, here we can see here the achaotic windows here, and when we apply the state feedback control, we can see that after state feedback control, the chaos is reduced. It means the complexity is reduced here. Similarly, the hybrid control method, there's a hybrid control method. Here the same thing. I'm not going to discuss the hybrid control method. It's a kind of the state feedback and the pole placement technique. We can delay the chaos in this kind of the control method. And here, if we talk about this diagram, flip bifurcation with respect to B, so you can see here for this set of parameter A equal to 3, C equal to 4, M equal to 0.4, and B equal to 2, there is a cascading effect of the period doubling. There's a period doubling. And now for the same values here, the control bifurcation diagram, because there is no chaotic window here. So this is the control, chaos control. And similarly, we apply the effect of pre-diffuse also, because the M is the pre-diffuse. So here, if we talk about this diagram, here M equal to 0.4, then it shows the flip bifurcation, and there is a chaotic window between 3.5 to 4 when the M equal to 0.4. And here, when we reduce the value of pre-diffuse, M equal to 0.05, there's a control diagram, there is no chaos. Chaotic windows disappeared. So this is the beauty of the chaos control in discrete models. Now I take another continuous time model to show the codimension 2 bifurcation and the resonance bifurcation. because the time is running fast, so I am coming to direct the continuous time. I take the continuous time model. So simple two species load ka ultra model, dx over d tau and the dy over d tau, the lx 1 minus x minus gamma xy, and dy over d tau equal to beta xy minus delta y, where alpha is the intrinsic growth rate of species, beta is the conversion rate, gamma is the per capita searching efficiency of the predator, and delta is the predator rate. So simple load ka ultra model. And we introduce here a harvesting factor. So here it is minus hy, h is the harvesting parameter. And finally, we discretized this model by using piecewise constant approach. The piecewise constant approach is better than the forward scheme because it explain the overlapping generation in well manner. So I applied the piecewise constant approach here, and this is my discretized model, xt plus 1 equal to xt to the power alpha 1 minus xt minus gamma yt. Here our term in the exponent. This is the difference between the Euler forward Euler discretization process and the piecewise constant argument approach. And similarly, the yt plus 1 equal to yt exponent beta xt minus delta minus h. So now we can write our model in the map form. This is the mapping. And there the fixed point, the trivial fixed point E1, 0, 0 always exists. If beta equal to delta plus h, the map has the axial equilibrium point E2, 1, it means the no predator species. If beta greater than delta plus h, then the map has a unique positive fixed point E3 star. And if beta greater than delta plus h, the map 3 has no positive fixed points. So here these are the fixed point, and around this fixed point, we will explore the system that which kind of bifurcation occurs in our system. So these are the conditions. For these condition, when the eigenvalues less than 1 or eigenvalues less than 1, and these are the condition, then the system shows the stability, it means the sick behavior. Where the one eigenvalue is less than 1, another is greater than 1, there's the saddle. So this is the table regarding the dynamical properties of the system. And now the co-dimension 1 bifurcation at E3 star. So here the period doubling bifurcation, as I discussed in the last model also, period doubling bifurcation for beta equal to 1 and for beta equal to this, lambda is not equal to, for this condition, the period doubling bifurcation. And the Niemark-Saker bifurcation, for this condition, Niemark-Saker bifurcation occurs in the system, in the model. Now the co-dimension 2 resonance bifurcation. That is the new thing compared to the last model. So co-dimension 2, it means the 1 is 1:3 and 1:4. So 1:2 sometimes it is denoted by R2, 1:3 R3, 1:4 R4. So these are the resonance bifurcation when the two parameter alpha and beta vary. If we talk about here we make the co-dimension 1 bifurcation, we make changes in only the beta. And here we make the changes in beta and alpha, both parameters. That's why it's the co-dimension 2 resonance bifurcation. So the condition that 1:2 resonance bifurcation, if alpha equal to this and beta equal to this. 1:3 resonance bifurcation for this condition, and 1:4 resonance bifurcation occurs if this condition hold. And if we talk about in terms of eigenvalues, so I already discussed that how the eigenvalues changes and for which kind of the eigenvalues this kind of bifurcation occurs in my introductory part of this lecture. So these are the model parameter when we alpha equal to 2.05, gamma equal to 1, delta equal to 0.4, h equal to 1.2, and very beta as a bifurcation. First, I would like to show the co-dimension 1 bifurcation and the Niemark-Saker bifurcation. It means this bifurcation occurs with respect to one parameter, and that is beta. So Nemack-Secker bifurcation, it means a simple limit cycle, and then this is a invariant curve. This is the closed invariant curve, and there's a chaotic windows and with intermittent quasi-periodic windows. So this is Nemack-Secker bifurcation diagram, and in the figure B, there's the Lyapunov exponent. As we know, the Lyapunov exponent show the rate of convergence and or divergence between two trajectories. And here, as because there is a chaos in the system, that's why this the maximum Lyapunov exponent corresponding to this Nemack-Secker bifurcation. That's why you can see here that the eigenvalue, the blue line, it crosses the zero, that the zero. It means the value of the Lyapunov exponent is positive. So if there is a positive Lyapunov exponent, it means this is the confirmation of chaos in the system. This is the resonance 1:4 resonance bifurcation diagram. How it is 1:4 resonance? You can see here that after one, the single line, it is split into 4 lines. You can see here. So 1:4, because there are the 4 branches from one branch, and followed by the wide range of chaos from the around the 2.62 to 2.7. So this is the 1:4 resonance bifurcation with respect to beta and alpha equal to 3.25. As it is the co-dimension 2 bifurcation, so that's why there are 2 changes in the 2 parameter, and this is the corresponding maximum Lyapunov exponent to A. As this, it has the chaotic window. That's why here we can say that the blue line of this MLE cross the zeroth line. It means it has the positive Lyapunov exponent, which confirm the essence of chaos in the system. So this is 1:4 resonance bifurcation. Now again, I apply the state feedback method here again. So I take a consider polynomial function to control the chaos V11, V1 to preserve all 3 fixed point of map 3, where V1 and V2 are constant here. V1 and V2 are constant. So this is my controlled system. Here you can see when we talk about earlier model where we put the UT, and here we put the CT in the exponent. E to the power alpha 1 minus xt minus gamma yt plus CT. CT is my polynomial function or controller, right? So by using the Zuri stability criteria, which is it's very analogous to because the Routh-Hurwitz criteria. So for Nemack-Secker bifurcation, we choose the parameter V1 and V2, and for 1:4, because in this model I show 2 kind of the bifurcation diagram: co-dimension 1 bifurcation, Nemack-Secker bifurcation, a co-dimension 2 bifurcation, 1:4 resonance bifurcation. And for 1:4 resonance bifurcation, we choose the value and V12. So by satisfying this stability condition, we choose this value of V11 and V12 for different kind of bifurcation. So here, now I'm going to show that what is the role of the controller. So this is the controlled Nemack-Secker bifurcation. How this is controlled bifurcation? If we talk about this kind of the diagram, here the Nemack-Secker bifurcation diagram, you can see a wide range of the chaotic window here, like from the 2.5 to 3.5. A huge range of chaotic window for these value. And when we apply the controller for the by taking a value of V11 equal to 5.75 and V12 equal to this, the chaotic window reduce or disappear and the system goes to stable side. And similarly, this is the diagram B, controlled 1:4 resonance bifurcation diagram. And you can see if we talk about 1:4 resonance bifurcation, this diagram. You can see here that here after one branch 2, there are split into 4 branches. and there it is a from 2.62 through 2.7, a wide range of the huge window. And by applying the controller, by using the value of V11 and V12, we can see here there is no chaotic windows and the chaos is stable. Chaos is reduced and complexity is disappeared from the system. So this is the beauty of the control of chaos. And show the effect of harvesting, because I take the value of the harvesting minus hy. There we took the h equal to 2.01. Earlier, when we talk about this kind of diagram, here the h equal to 1.2. So here we can show the effect of harvesting also. So now when we increase the value of harvesting, h equal to 2.01, we can see that the chaos is reduced in the system. So this is also controlled Nemack second diagram when h equal to 2.01. So we can say that the harvesting also a controlling effect in the model. Okay, so harvesting also may control suppress the chaos or complexity in the model. So this is the summary of the wide range of dynamical behavior, including codimension 1 bifurcation, resonance bifurcation, and chaos are obtained in the system. Predator harvesting may control the chaos in the system, and the state feedback method is applied to control the chaos in NSB and 4-cycle resonance bifurcation. And ecologically, the prey-predator species coexist up to 4th order, because I am talking about 1:4 resonance bifurcation here. So ecologically, the prey-predator species coexist up to 4th order in the stable high periodic cycle. These are the reference which I used in my research. So that's all. That's all from my side. And now questions, audience.
Hello, ma'am.
Yes.
What is the geometric meaning of Bogdanov-Taken's bifurcation?
Sorry?
What is the geometrical meaning of Bogdanov-Taken's bifurcation?
Bogdanov-Taken bifurcation is a kind of the cusp, right? So it means when we get a limit cycle, and from the limit cycle we obtain a cusp. So that is why it is called a codimension 2 bifurcation. We have to change this. When we find the limit cycle, a limit point in the model. So because the limit point is we can see the fold bifurcation, we can see the codimension 1 bifurcation. We make the changes, and the trajectory show the cusp behavior. So this is the we can say the BT is a kind of the cusp.
Is it same in continuous dynamical system also?
Yes, it is same. Difference between the continuous and the discrete is only one, because the threshold in the continuous, the threshold value is 0, and here the threshold value is 1. So the hyperbolicity threshold value is the difference. Otherwise, the BT both in when we talk about the continuous or discrete, both are same.
Yes.
Geometrically.
Thank you.
Yeah. Okay. Yes. Okay, you can write me on my mail also, because I'm associate professor in UPV The mail ID is given there. You can send me a mail, or you can ask your queries. Okay, Professor. I think audience have no doubts, no questions. Okay. Okay, fine. Okay. Okay, thank you.
Yes, it is audible. Thank you. Thank you very much, Krishan Panda Das. First of all, I would like to thanks to Dr. Das for inviting me and to share my knowledge with all of you. So let me share my screen with you. Can you kindly confirm, please, whether the screen is visible? Okay. Okay, thank you. Thank you very much. So today, I will try to explain you what is the nature-inspired algorithms, what are the various features of that, and where we can see its application in our day-to-day life. So you all might heard about the nature-inspired algorithms, which is frequently used by the many of the researchers in day-to-day life to solve your complex, non-convex, and the non-differentiable optimization problem. So basically, the nature-inspired algorithm is used. This algorithm is basically used for developing an optimal for finding an optimal solutions for the non-convex. First of all, it's a non-convex. Second is it is if it is a non-differentiable function. Because we all know if the function is differentiable, then you can easily optimize the function or optimize the problem by using a second derivative to be first derivative to be the 0 and second derivative to be less than or greater than 0. What is the content I have chosen for this is I will simply, firstly, I will give you the importance of this AI or the nature-inspired algorithms. Then we will see what are the various existing methods and how they can overcome it. Finally, we will see what are the classification of the beta heuristic, and I will give you the 3 major direction. This direction will help you to think how you can develop the new nature-inspired algorithms in your future research work. As my friend introduced me, I myself, Dr. Hishkar, I am working in the Department of Mathematics, Thapar Institute, Patiala. You can contact me either of my email IDs or you can simply follow my YouTube channel for various nature-inspired algorithms and their MATLAB code. First of all, what is the overview of the nature-inspired algorithm? So we all know the artificial intelligence. That's a part, one of the nature-inspired algorithm is one of the part of the AI, which has a wide range of the applications. Many applications are there, and which the nature-inspired algorithm is one of the classified part of the artificial intelligence. One of the most beautiful example of the nature-inspired or the computational intelligence is to find the inexact solutions from the NP complete problems. That means whenever you have a non-convex problems, whenever you have a non-differentiable function, how you can find the optimal solution. That is always a challenging one. What is the meaning of the NP hard problem? When you are trying to find the computational complexity of the algorithm. Like we all from the mathematics background, so we all know the Newton-Raphson method for finding the root of the equation has quadratic convergence. So that means you are able to find the time period when you run the MATLAB programming or C programming or Python programming. But what will happen if you are unable to find the solution in terms of the polynomial time period? That is called as the NP hard problems. For example, very well common problem is the traveling salesman problem. If you have such number of the cities, and we all know what is the traveling salesman's problem, you start from any one of the city. You start from the one city. Let's say this is my start city, and your target is to visit all the cities one time. Fine. How you can move on that? You may start from this to this. You may go from this to this. You may go from this and then this and then this and then so on. Or you may go from this to this firstly, then this to this and so on. So, but question arises is, how many feasible paths you have? How many feasible way you have? So how you can find the number of the feasible ways? It is obvious that it's a very, very difficult task. Fine. So if I simply take the 20 cities, like city 1, and this is my city 20, fine. Then how many possible way you have, or how you can optimize yourself, so that you can start from the one city and reach at this 20th city by visiting one city at one time each city. How many possible way? Can you guess about that? Fine. How many ways are there? So that means if you talk about the n factorial, then it has this much path for you. You can see 2.43 into 10 raised to power 18. This much paths are there. For example, the first path is you can start from this, this, and this. This is my first part. Second path is you can start from this, then reach at here, then reach at here, then this, and so on. And many more are there. So how many paths you have? You have this much path. So kindly see that this is a very, very large number. So it is not always possible for you that you can go from the one path, second path, third path. Out of this path, you will get the optimal solution O1, you will get the optimal solution O2, and optimal solution of this much. Out of those optimal solution, you can find the feasible one or optimal one. That is not an easy target for you. And look at that. Right now, I consider only as a 20 cities. If I consider as a 200 cities, then this number is out of the imaginations. So for that, such problems is called as the NP hard problems, because the growth is my exponential area. So that means we are unable to find the optimal solution in a most reasonable time. So for that, we are able to know the artificial intelligence or the nature-inspired algorithms. So the exact methods, what are the exact methods? We all know that is my quadratic method, or we called as a Lagrange multiplier method. We all know about the KKT conditions. Fine. We all know about the Wolf method, or many more are there which you have studied in your optimization techniques. All have the polynomial time periods. But whenever we are talking about the real life problems, we always have many problems, many variables which are always be the continuous natures. So that means the number of the decision variables, sometimes we have the indefinite. So for that case, the target is to choose the right path, choose the right algorithms, so that we can get the exact solution in a reasonable time. So whenever the number of the decision variable is a very large, then you are unable to find the exact solutions. Fine. Or you are unable to get the optimal solution. Feasible solution, you can easily find it, but the optimality, you can't guarantee about that. So for this case, we discretize this soft computing or the computational intelligence into the subfields. The first one is the nature-inspired algorithms. Second one is the fuzzy logic system. And the third one is the neural network, or I call it as a fuzzy logic, neural network, and evolutionary computation. Fuzzy logic is always used when you have uncertainty in your information, while the neural network you can use when you have tried to predict to minimize the error. However, right now I will explain you what is the nature-inspired algorithms. So I again discretize this into the three component. One is the fuzzy logic, machine learning based algorithms, and the evolutionary computation. These all are the part of the soft computing or computational intelligence. That is my CI. I again discretize this evolutionary algorithms. This machine learning is again called as the neural network based algorithm, because the target of the machine learning is to minimize the error. I again discretize the evolutionary computation into the three parts. One is the evolutionary algorithms, swarm intelligence, and the meta-heuristic algorithms. Remember, you all know there are the two kinds of the methods. Like you all know when you solve the system of the equation, you have exact methods, which we studied as a matrix method or the Cramer rule. When you call as the approximate method, we always call as the Gauss-Seidel method, Jacobi method, and many more. That means it will give you the approximate solution up to the some desired accuracy. When we call as the exact method to optimize any of the things, what is the meaning of that? You will use the Lagrange multiplier, KKT conditions, or any of them. You call as a steepest descent and many more of them. But if you look about that, all these conditions will require the derivative of the function. Fine. But this technique will fail to solve when you are unable to compute the derivative of the function. That means that method requires the non-convexity, non-differentiable, and here. Whenever such conditions will satisfied, these methods are fail to find the optimal solution. So the challenging is there, how you can tackle the problem which is non-differentiable, non-continuous, non-convex, and many more are there. So for that, we will see the work on the unstable. So we always look for the real-life problems where our target is to identify the variables which may be of the continuous, integer, binary, or many more are there. Then we will look about the solutions to pick them. So for that, there are like traveling salesman problem is a very expensive problem. How you can solve these problems? So the earlier methods, that is the exact methods, are always guarantee about the optimal solution in the reasonable time. But make sure whenever the problem is a NP hard problem or whose polynomial, whose complexity is not measured in the time period, polynomial time, that means when there is no polynomial time exists, that is called as the NP hard problem. Or when the size of the problem is increases, then the time complexity will also increase. So that will take you the last computational time. So that means we are always looking from the optimization problems, which will give you the reasonable time period. So all this motivation will help you to encourage us or help us to encourage to learn what is the meta-heuristic techniques. So what is the meta-heuristic techniques? So first of all, meta-heuristic techniques is the approximate algorithm. It will not give you the exact solution, but it will give you the approximate solution under some accuracy. So that accuracy, you may have 10 to the power minus 10, or you may have the 10 to the power 5 as per the desired level. So a kind of the algorithms that is approximate, which is called as the meta-heuristic. Meta-heuristic is widely used in the last 3 decades because of the simplicity, easy to implementations, and most important thing is there is no need of the derivative function. So we can optimize the function without using the derivative. And also it avoids the local optima solution. The two major features, when any one of them will study about the meta-heuristic, you need to focus about the two major parameters. First one is exploration and second one is exploitation. As the name suggests, explore. Fine. This means is the explore and this means exploit. Fine. What is the meaning of the explore is you have to ability to discover the new searching solution. For example, if I say this is my searching space, my solutions are here. Fine. And I start from this. This is my initial guess. And this is my optimal solution. Say this is my optimal solution. But we never know this is my optimal solution. Fine. So I try to find the optimal solution near to them. So what I can do, I can start from here, try to reach at this by some approximation. Then from this, I can reach to the next approximation, then to the next, and so on, and until you will get the near to the solution. So this exploration means we can extend my feasible area to this domain so that I can reach the optimal solution from this side also. Fine. From this side also. So that means we can discover the new searching area. On the other hand, exploitation means we can find the best solution from the region. That means, for example, if you have the optimal solution like here, we know this is my maximum. This is also the maximum. Fine. But we call as the local maximum. So if we are searching from this domain to this domain, from 0 to say -4, we will get this optimal solution. But if I take as say 3 to 9, we will get this optimal solution. So what is the exploitation is we will find the best solution by expanding the availability. That means if we expand the domain from -7 to 11, I can find the best one. That is a maximum among them is my here. So that is called as the global optimal solution. So remember, whenever you are talking about the meta heuristic techniques, your target is to balance the exploitation and exploitation. Remember the term best is it is not the global, but we are talking about the best. Now, the meta heuristic method is widely used because the target is to give the approximate solution. And you can get your approximate solution within the 10 iterations, maybe the 100 iterations, but we will get the reasonable time. Now I can classify what are the various meta heuristic techniques. So first of all, what is a heuristic? Heuristic techniques is a classical technique which will not give you the guarantee about the optimal solution, but that will solve the problem, but will not guarantee about the solution. Hyper heuristic means we can choose, for example, what is the meaning of the heuristic? Suppose you have the different algorithms. I have the problem, say maximize fx, subjected to some constraints, less than 0 and some feasible area. Now, you can see you can solve this problem either by using steepest descent method, fine. You can use by the KKT conditions, and many more are there. So these all are my heuristic algorithms. What is a hyper heuristic is? I can choose one of them. So this is the heuristic which will help you to choose whether I can choose the algorithm 1, I can choose the algorithm 2, I can choose the algorithm 3, and so on. So how you can choose which algorithm will be applicable, like you know the PSO algorithm, you know the genetic algorithms, and so on. But which one is the best algorithm for your problem? That will help you, that will give you by the hyper heuristic algorithm. So whenever you have a high level problems, you can manage the low level by selecting the heuristic algorithms from the available one. The same problem we have. Suppose our target is to complete this problem. I have the person 1, I have the person 2, I have the person 3. So if you choose the B, how you can think about that the B will be the right person to solve the problem? That is called as the hyper heuristic. That is, choosing the best one is called as the hyper heuristic. Or we can also generate the new one based on the previous knowledge. Okay. The hyper heuristic will always either the single one, or you can take it as a combination of the low level. The fundamental difference between the hyper heuristic and the meta heuristic. Look at the word of this. The hyper heuristic search for the good problem, while the meta heuristic are searching for the good solution to the problem. They are search to solve the problem while they are searching for the problems at the other hand. So look at the problem of they are searching for the good heuristic while the meta heuristic is searching for the good solution. Again, I will tell you, if you have the optimization algorithms, say A, B, and C, which one is the best one for your problem? Which one is the best one from your problem? You can say A is your best one, B is your best one, or the C that is chosen by the hyperheuristic. Once you choose, say B is my best algorithm for the problem, that is the hyperheuristic, then you are talking about the solution that is given by the meta heuristic. This motivation will help you to perform in a significant manner that I already told you is a simple manner. So we always look about the more exploration that is will give the poor performance. Okay. So now how you can classify this meta heuristic? Remember, our target is always to find the optimal solution. So solution will always give you by the meta heuristic. Now, there are the basically, I discretize into the 6 part, but it may have more than one. First one is nature inspired or the non-nature inspired. Second one is the population or the single base, dynamic and the static, one single and the various, and many more are there. What is the difference between them? What is the nature inspired is? We all know the genetic algorithm which is inspired from the genes. Fine. Ant algorithm which is inspired from the behavior of the ant. You can see about the behavior. This is my ant which is moving on this, which are always moving in the same direction. So the algorithm which are inspired from the nature, we call as the nature inspired algorithms, while which are not nature inspired, we call as the for example, the taboo search and here. What is the population and the single base? We all know when you are using the Newton-Raphson method or when you are using the steepest descent method, how you can start the algorithm? You start with the initial guess x naught. That means you are chosen as a 1 point formula. You are chosen only as a 1 point, that is a single point. But if instead of the single point, if you choose as the population, like if you choose 3 as the starting point, fine, then we call as the population-based algorithm. So genetic algorithm is a population-based algorithm because it used many initial points at the starting point. Like if I say this is my complete feasible area, I can choose this 7, 8 points are my feasible point. The algorithm which is only based on the single solution is called as the single point search. As the name suggested, the dynamic, which are changes with respect to the time, while the static means which are not changing with respect to the time. One single, that is basically the topology. So if you consider about the single topology or the ring topology, star topology, that you can define as the behavior of this. All these algorithms are to update the solution space. Your target is to update the solution space with the help of the behavior of the exploration and exploitation. Okay. The memory based, we all know some algorithms have saved their memory, someone not. So whether they will use the memory or not, we call as this one. So for example, the Markov process, we all know the stochastic process will always use the memoryless property. So that means whenever they are trying to find the next equations, they just use like if the person is here, if the person is here, if the person is here, then after this point, the person may move on this, the person may move on this direction. So it means the direction of this person will totally dependent on here, but not on this. That means this is a memory-less algorithm. If you have the long-term and the short-term memory, then you can again define as the decision based on their parameters of the various algorithms. Now, the use of this memory, algorithms is one of the fundamental of the meta heuristic algorithms, because we always try to look about the optimal solution. if I found the optimal solution at the, say, third iteration, I can preserve that equation in our mind or in our memory and compare with the seventh iteration, which one is the best one among the others. What is the main three directions? How you can find, how you can propose your new algorithms. So remember, the first one is you can, whatever the parameters you have in your algorithm, you can control that parameters, you can update that parameters, and then you can develop the new algorithms. That means if you have the initial algorithm like PSO, genetic algorithms, and many more, you can update their parameters and develop the new algorithms. Second one is you can hybrid the algorithms. Like if you have the PSO algorithms, you have the genetic algorithms, you can take the weakness of these algorithms and you can update their weakness by taking the advantages of the PSO. And then you can club them. You will call as the PSO GA algorithm. That means you can hybrid the algorithms by taking the benefits of the other one. That is the direction 2. You can work in that direction. The third one is you can introduce the new algorithms like by with your name or by the other nature inspired algorithms. Now, this nature inspired algorithm is basically divided into the 4 categories. First one is the evolutionary algorithms, swarm intelligence, physics-based algorithms, and the human-related direction. So these all categories are fall under this direction 3. How you can define the new algorithms. So for example, these evolutionary algorithms are inspired from the biology. So any of the algorithms which are inspired from the biology, we discretize into the category of evolutionary algorithms. Whenever you are trying to look about the nature or some insects or the animals, then that is called as the swarm. Whenever you are looking about the swarm, like a rat, like pigeon, fine, like whale, fine, the corresponding algorithm we have defined is fall under the case of swarm optimization. Similarly, if you look about the physics based, like we all know, I hope you all remember this very famous law. This is called as the gravitational force. And if you think about the gravitational force, and you can define the algorithm that is called as the gravitational algorithm. And that algorithm is defined from the physics base. And the last algorithm that is based on the behavior of the human, that is called as the human being behavior. What are the classifications of them? The evolutionary algorithms like the gene, they are inspired from the genes. Fine. This is called as the genetic algorithms. What is the swarm algorithms? We call as the ant colony because they are behavior of the ant. What is the particle swarm? They are behavior of the birds and many more. What is the physics-based algorithms? We call as the gravitational force algorithms. Fine. Human-related algorithms, that is the teaching learning based. We all know that teaching learning is the mutual understanding between the students and the teacher, that is based on the human being. Look at that. If you are called as the swarm intelligence algorithms, ant colony, population based, flower pollinations, bat algorithms, dragonfly, all are the behavior of the swarm. So that's why they are discretizing into the swarm intelligence. If you call as a human related behavior like neural network, sine, cosine, teaching learning based algorithms, all are the behavior of the human related algorithms. And these are the recent trends about that. Many of the problems and many of the articles is published in these days based on these different behaviors. So this is the basic idea about that, how the nature inspired algorithms will work in these cases. If you want to find some more detail about that and their MATLAB code, you can simply go to my YouTube channel and you can learn many MATLAB codes and the algorithms behavior of this one. And you can see the many algorithms I have explained with that. If you have any doubt, you can ask me. Thank you very much, audience.
Hello, hello, hello. May I ask you first of all, thank you for the nice presentation. I have a simple question. Can the optimal control problem be solved by meta-heuristic algorithms?
Yes.
Optimal control problem
Yes,
can be solved by meta-heuristic algorithm?
Yes, definitely. A very common problem is the PID. It's a well-known problem, and already many of the articles are published and solved by the meta-heuristic algorithm. You can solve it easily.
Okay. Thank you.
Because whenever you are working on the control problem, your target is to optimize the problem. Fine. So once you optimize them, then you can easily use the meta-heuristic algorithm.
Yeah. Okay. Thank you.
Oh, welcome. It's my pleasure always. Okay. My pleasure. My pleasure. Thank you very much.
Yes, I am here. Hello. Okay. Am I audible? Okay. Okay. So let me share my screen. So first of all, I would like to thank the organizer for giving me opportunity to speak on this topic. And so I will talk about some of the things or some of the theory which is related to delay differential equations and which is usually applied in mathematical biology. So if we talk about the delay, why delay is important, so let me first of all see what is the importance of delay. So in many modeling process that we have, we know that we generally assume that every process is governed by the principle of causality. That means every action, whenever it takes place, it has a instantaneous reactions. So there is no, in fact, there is no lag between the action and reaction of any process. So whenever any process takes place, its outcome is clearly visual and it is clearly instantly visual to me. For example, whenever I have a pain, some kind of pain, let us say headache, and if I take a medicine, that medicine will affect me or take me relieve my pain instantaneously, which is not true. So in general, every process involves some kinds of delay. So whenever we talk about the delay or we introduce the delay, we come across the a very beautiful you can say type of differential equation which we call it delay differential equations. So when we talk about a ODE counterpart of delay differential equation, which is ODE and PD, so ODE and PD are basically just a representation or a approximation of the reality, which is not actually true. So every process which is actually modeled by ODE and PD is basically a approximation to the real world, because everything that happens in nature has a some kind of delay. Okay, so that's why this OD, we call this OD and PD just as a approximation. So when we say when we talk about some of the problem, it is meaningless actually not to have the dependence on the past, that is dependence on the history or the consideration of the delay. And the history of using delay differential equation or differential equation depending upon the past state is rather old. It is very old. It's basically coming from a very actually a starting time, and basically you can say that its work basically started at the time of Volterra. So when Volterra was talking about the pre-Peter model, then of course this delay introduction took place. So for example, whenever we have a process such as a acceleration, deceleration, which actually takes a little time to compare to the time needed to travel the most distances. So time involved in the biological process such as gestation and maturation can be substantial when compared to the data collection times in the most of the population studies. That means that whenever we consider the delay, sometimes the delay is not substantial and sometimes it is very substantial. So whenever it is substantial, it has a very large effect on the system. So consideration of delay in the most model becomes indispensable. That means it is very important to consider those kind of delay whenever the order of the time delay is of comparable magnitude with respect to time span of the situation. So in the domain of our problem, time domain of the problem, if the delay consideration is substantial, then only we can take the effect of delay in our model. So let me first of all talk about what is the consequences of delay. So suppose we have a process which has a delay or which has a lag. So what is the consequences when we introduce the delay? So it many times it has been observed that introduction of a small amount of delay of the discrete time can destabilize the otherwise stable system. Okay, so whenever you have a stable system which is otherwise stable, in absence of delay, if you introduce a small delay, the system becomes unstable in nature. So underlying system of differential equations are much more challenging, because this is one of the most important features of the delay differential equation, that whenever you introduce a delay, the system becomes a system of delay differential equation, and it is very challenging to work on this or analyze this model which is dependent on the delay. So, and of course, the model that you have got by introduction of delay will become more nearer to the originality. That means it is now more natural to imagine that it is actually the original process. And also the system that we obtain is highly nonlinear. That means whenever you have a linear system, even though the system ODE system may look like it is linear, but your delay differential equation, which is of course coming as a linear one in case of absence of delay, the delay will become, or delay it will take two in highly nonlinear system. And also it is of infinite dimensional nature, even if the system maybe appears to be one dimensional or finite dimensional, then also the system is of infinite dimension. So these are important consequences of the delay system. So let me start with a very basic model of the delay. That is, it's an example of the delay differential equation where it can be actually used. So here we use this delay model as a drug assimilation model into the blood. So whenever we take any drug, how the drug get into a stomach, and from the stomach, it's through digestion, it goes to your bloodstream. So this is how we can model this system into with the help of delay differential equation. So let us say X and Y represent the amount of drug that is present in the stomach, that is GI tract, and the Y which is in bloodstream. So we say that we are adding the constant amount of drug, that is constant at the constant rate, the drug input into your stomach, or we are taking the drug at a constant rate I, and at the same time this drug is being digested from the stomach at the rate K1. So K1 is the rate of digestion of the drug from the GI tract. After certain time, whenever digestion takes place, digestion involves a certain time of lag. Let us say digestion has a lag of time t, that is, it has a delay of time t. So whenever a delay happens, or whenever we introduce delay, the drug which is in the bloodstream will be coming from the GI tract, which has been already there in your stomach, and which has digested from the stomach. So the drug inside the bloodstream will be just effect of the drug that were there previously in your GI tract. Okay, that is in the stomach, and after time lag of t, it got digested, and that's how it appears in the bloodstream. And K2 is the rate of drug assimilation from the bloodstream. So this is a very simple model, which is of course a linear model in absence of delay. But if you consider the delay, it's basically a nonlinear model. It is not usually solvable by algebraically. That means you cannot solve completely here analytically, but you can apply the nonlinear problem here, nonlinear you can say numerical problem here, to get the solution of this kind of equations. Again, we know that a very important equation in the mathematical biology is a logistic growth equation. So here, in this case, we assume that the any species, which is actually single species, grows with a logistic growth rate. So R is the basic reproduction rate, and K is the carrying capacity. So in this case, you know that the system always stabilizes to a level x is equal to k. So x is equal to k is basically an equilibrium point, which is called a stable equilibrium point for this kind of model. So every solution will tend to the k point, that is, every solution will approach the value k. So in this case, you will see that the logistic equation or logistic growth model always have a stable points. Okay, it doesn't have any unstable points. There are point which is called 0 point, which is also unstable. But every whatever the initial value you take, our system always goes to a stable equilibrium point, which is x is equal to k. Now, what happens if we introduce a delay in this model? So if I introduce a delay, so by the way, this is the simulation of the OD model. So you can see here every solution approaches the value x is equal to k in the longer run. So x is equal to k is a stable points in this case. But if I introduce a delay, so delay is could be because of the delay which is due to the time which is between hatching and the formation of egg. So in this case, if I introduce the delay differential equation for the logistic case would be given by this. Now, if you simulate this model, you will see that there is an interesting thing which comes in here, which is basically the oscillation. So whenever, so as we said that your original OD model doesn't have any unstable solution in this case. So system always stabilizes to a stable solution, but here the logistic delay differential equation might have a somewhere unstable solution in the form of oscillations. So your delay differential equation will give rise to oscillation in this case, whereas your OD model doesn't have any oscillation at all. So this is one of the thing that delay introduces in the model. So delay can sometimes lead to the unstable solution, or it can destabilize the system which is otherwise stable. Okay, so I can give another example. Here I have formulated one equation, which is a delayed model for HIV infection. So here there are three important state variable here. U1 is uninfected CD-T cells. So uninfected T cells. Then U is infected T cells, and U3 is the virus one. So here I am assuming that whenever the infection, whenever the HIV interact with the uninfected T cell, it gives rise to a infected T cell, and this infection, there is a time delay. So tau is a time delay between the interaction and between and to the time which infected T cell is produced. And because we assume that the distribution of infected T cell could evolve as a exponentially distributed, so there will be some uninfected T cell which will be die out, and whatever the remaining T cell left in this case would be considered for the further growth of the virus particle. So after the lysis of one infected HIV T cell, uninfected T cell, there is a production of n number of infected or n number of HIV particles in this case. So this is a kind of infection model which happens in a HIV model. So in this case also, if you simulate the model, you will see that the delay can introduce a substantial amount of oscillation in the model. So let us talk about some of the features of the delay differential equation. So there are terms which is called differential order. So differential order is nothing but the order of the highest order derivative occurring in any of the differential equation, delay differential equation model. And difference order is the one less than number of distinct argument that happens in the model. So if we talk about all the three examples, the example 1 is of differential order 2 because highest order derivative is 2, while the difference of order is 1, while while in 2 is having differential order 2 and difference order 1, or differential order 1 and difference order 2. So this is a term which is used in delay differential equation. Similarly, we can define a general form of delay differential equation involving there could be n number of delays in the system depending upon how many state variable you are taking. So you can form a general a differential equation which is in n dimension and which has a n delays. So there could be n delays in the model itself. So we can write the general n delayed differential equation model or system of differential equation which happens in Rn by this one. Now, if you want to solve the differential equation, you need to have a initial function instead of initial value, and this initial function need to be defined in all the t range starting from you can say the maximum delay till t0, that is starting point. So depending upon if you define this function, you can solve this differential equation easily by use of some numerical technique. So here phi t is called history function, or you can also call it as a initial functions. So the space of solution is infinite dimensional, as I told you that whenever we talk about delay differential equation, its dimension is coming to be infinite dimension. Okay, so general differential equation have this form, and this function need to be continuous and need to be there in the Banach space of all continuous function. And once you have this function defined, and then you can talk about the following theorem, which talks about when the solution will have a will exist, and when the solution will be unique, and when the solution will be positive, have a positive solution if your system is a physical system. So for existence, in the domain, f need to be continuous in the domain, and this initial condition, if the f is continuous in the domain, then for any initial condition in this domain, the solution will be there. That means solution will exist. But in addition to the continuity, if the function becomes Lipschitz, then the solution is of course unique in the for the case of delay differential equation. So just like ODE, we have a corresponding theorem for DD as well, and the same thing can be extended for delay differential equation also. Now, for existence of positive solution, we need to identify, we need to write this equation in this form, and we need to ensure that this function has all this function satisfy this coordinate condition. For this, then the system will always have a positive solution if your solution initial solution is positive. So if your solution is positive, initial condition is positive, your solution will also be positive. So this is called positiveness of the solution. So there are other types of the differential equation, delay differential equation, which frequently occurs in nature. So if we consider this general differential equation, delay differential equation, here if we note there are constant a0, a1, b0, b1 in this case, and the function ft. So if a0 is non-zero and a1 is 0, we call it as a retarded differential delay differential equation. If a0 is 0, that is a0 means that the a0 non-zero and a1 is also non-zero. That means the derivative the multiplier or the coefficient of the derivative y dash t minus tau is non-zero, and this is also non-zero. We say that is a neutral type of delay differential equation, and for other case it is called advanced type. Now there can be different types of delay also. The delay parameter, we have a constant delay differential equation. That is where the delay is constant. There can be time dependent delay differential equation also, and there can be a state dependent delay differential equation also. So although the constant time duration delay differential equation is most common, but these are also there, but these are basically very, very difficult to analyze. So we can talk about what is the difference between the OD and DD in a sum up. So OD have a, as we know, it needs initial value, whereas DD needs a history function which is defined in this range. The history function are not unique for the same solution, and there exists an initial discontinuity in the derivative, in the first order derivative. So this is basically very, very important thing to note in the delay differential equation, that it has a discontinuity in the first order derivative, and also the discontinuity can propagate in a successive steps whenever you have a delay differential equation, and the delay can stabilize or destabilize system. Whereas the destabilization is most common, the stabilization is less common in nature. So as I already told you, that whenever you have a OD and your solution is stable, the delay can destabilize the system, that that we have just seen in case of a logistic delay differential equation. DD can be reduced to OD if there are no non-zero delay terms in this case. Okay. So one important thing to note, that a small delay can have a large effect. That means, let us say this equation. Now this equation, if you talk about the solution of this equation, it is always asymptotically stable. But however, if you consider the counterpart of this equation as a delay differential equation, this differential equation is always unstable for any kind of delay. So this is one of the things that you can note it, that a delay can stabilize the system as well. Now, as I said, there is a difficulty in the solution of the delay differential equation, that whenever you consider the different solution, it has a discontinuity, and the discontinuity propagates. So if you consider the left-hand derivative of y dash t and right-hand derivative of y dash t, so it is not equal, so it is discontinuous. So it has a jump discontinuity in y dash t, and also just this jump discontinuity propagates, that is y double dash has a jump of tau, then y triple dash will have a jump of 2 tau, and so on. And discontinuity increases in the order of the entire differential equation, but generally they do not if there are delay terms in the derivative, that is neutral DD. So there are special cases of neutral delay differential equation, that this discontinuity can be avoided in many of the times. Now there are some basic theory which is associated with the delay differential equation. So one thing we say, that if you have this kind of delay differential equation, then there is a theorem which talks about the uniqueness of the solution function. So since A and B, which is the matrix, constant matrix, if since constant matrix is always a Lipschitz, so you can say that there is exists a unique solution function for this kind of delay differential equation. And also there are some exponential estimate on the bounds of the solution of this one, that whenever you have the real valued continuous functions and beta is non-integrable on this, then ut is defined by this, then you have this kind of this. So you have that the solution is ultimately bounded in some cases. There are some estimate for the solution as well. So similarly, the solution can be also bounded in some cases. So this is the theorem which talks about the boundedness of the solution. Now there is one important thing to important analysis in delay differential equation, that how to analyze the system in relation to stability theory. So most of the theory which is actually true for OD, this is also true for DD with some exception. in case of analyzing this characteristic equation. So in case of the delay differential equation, the characteristic equation can be given by this. So this is a general characteristic equation which you can obtain in case of a delay differential equation, and this is called a transcendental equation because the characteristic equation comes in the form of e raised power zj, and this is basically a transcendental function because whenever you say dz, whenever you talk about dz, the roots of this equation, then there are infinite number of roots for the characteristic equation of the delay differential equation at any of the equilibrium point. So if you linearize a system of dt at a certain point, your characteristic equation is going to be a transcendental function of this type. It is always of this type. So to analyze this the roots of characteristic polynomial, there is a theorem which is due to Pontryagin, and this says that if you want to talk about the solution of this differential equation, that is nature of the equilibrium point, we need to first substitute z is equal to iota omega and look for this type of equation. So that means we will separate the real part and imaginary part of this equation under the substitution z is equal to iota omega. So you will have some real part and you will have some imaginary part. Then the theorem says that if roots of 5, this one, your original characteristic equation, have all negative real part, because this is the criteria for the stability of the equilibrium points. We say that the equilibrium point is stable if it has all roots. The characteristic equation has all roots with a negative real parts. Then this theorem says that then all zeros of d1 and d2 are real, simple, and alternating, and this will be true. So this due to d1 and d2, you can analyze the nature of the roots of 5, that is your original characteristic equations. Similarly, there is a theorem for sufficient stability of the equilibrium point, that if all zeros of d1 d2 are real and alternating and simple, then inequality above is fulfilled, that is this inequality is fulfilled, then there is at least 1 omega for this for at least 1 omega, then you will have the sufficient condition for stability. Now although this theorem looks very easy to use it, but there is some difficulty because the theorem only holds in case of commensurable delay, that is if your delays are countable. Okay, if delays are non-countable, then you cannot in case of commensurable delay only this theorem is valid. Otherwise it has a it has a difficulty in applying that one. There is also one theorem, Severbrate theorems, which actually has an infinite series. You can say if your dz is of this form, then d1 d2 is this form. So then Routh-Zwitt criteria can be applied in some cases, but this is also not very good for the application point of view. So there is another theorem. Assume that d1 and d2 have no common zeros, then quasi-polynomial d is stable if and only pm is greater than 0. So this is basically with regard to this one. So this you can also apply sometimes. So impossible to apply, as infinite number of inequalities has to be applied in this case. So there is infinite number of inequality that will you obtain, and it is very difficult to handle this kind of one. So there is another theory which is domain division, subdivisions, which author can, any of you, if you want, you can search on the net and you will find some theory behind this one. And there are some other theorem which is related to frequency method, is also one of the things which you can learn. Now sometimes if you know the characteristic equation of delay differential equation, then there is some general theory which you can apply to find out the stability of any of the equilibrium points. So for that, if you have the linear system, let us say this, you have a linear system which you of course can get from the linearization by taking x is equal to c e raised power lambda t as a form of solution, then your characteristic equation can be given by this. So in most of the cases, the characteristic equation of you will see that this characteristic equation, this is a this is a transcendental equation, and since the characteristic equation has an infinite number of roots, but there is a very special things which talks about the stability of this theorem, that there is a sequence lambda g of the solution of 9 such that this holds as j holds, then real part of this will be negative. Real part of lambda g will tend to minus infinity as j tend to infinity. So in this case, you will see that there is a real number alpha such that all solution of 9 will satisfy this one, and there is only finite number of solutions in any vertical step in the complex plane. That means that the stability of this kind of differential equation, this kind of equation is only decided by finite number of solution of this equation. And the finite number of this equation, if because always if in always infinite number of equation, infinite number of roots of this equation will have a negative real part, only finite number of roots will have a positive real part, and those positive real part only decides the stability of this kind of equations. So you can talk about, you can always determine the stability as the following process. So you find out the characteristic equation first of all, and you write in this form, and you talk about when this equation has a purely imaginary roots. So when it has a purely imaginary root, you can substitute iota omega in this one, iota y, so you will get this equation. And because of this, if you set this one, you will find out the after some analysis that sine tau y and cos tau y is given by this one. So looking at the process, you will find out that the following theorem will talk about the stability of the equilibrium points at any of the equilibrium points of the delay differential equation in terms of p lambda and q lambda. P lambda and q lambda, we have already said that it is basically the polynomial part of the transcendental equation. So knowing that p lambda and q lambda, you can have the condition for the stability of the equilibrium point as the following. So if p lambda and q lambda has no common imaginary roots, okay, if consider this one analytic function in a real part, that is in a positive half, and satisfy the following condition, that is p lambda and q lambda has no common real imaginary roots. P of minus iota y is p of iota y, and this one is true. P0 and Q0 is not equal to 0. Limit of supreme of this is less than 1, and f lambda, which will be a equation, polynomial equation in y, which has a at most finite number of roots, real zeros. So then if you can determine the real zeros of this one, f0, so if f0 has no positive roots, then there is no stability switch occurs in this case of stability. That means the whenever the delay differential equation is stable at tau is equal to 0, it remains stable forever. And similarly, if fy has at least one positive root, then for each of them is a simple, and suppose it is of them simple, then tau increases. Then as tau increases, a finite number of stability switches may occur. That means whenever your equation, this equation has at least one positive root, then you can be sure that there could be a stability switch. That is, after a certain time delay, your stable system will become unstable system. So there are some theorems which is related to global stability. So I'm not going to talk about this because of the shortage of time. So I will talk about some of the numerical technique. You can talk. We can see in some of the software. For example, your MATLAB has a built-in package which is called DD23, which you can solve a system of differential equation like this having n constant delay. So in this case, if your system is given by this, you can always use DD23 to solve such kind of equations. So there is you can call the solution this solver by this following two technique. that is sol equal to dd23. Oh, sorry, this is 23. Sol is equal to dd23. Then you can create a dd file. dd file is basically write-in file which you can create. Lag is basically a input which stores the you can say all the time delays. History is a function which is stored history function, and t span is the time span in which you want the solution. So using this one, you can this solver calling technique, you can solve any kind of delay differential equation. So, and once you have a solution, you can call this kind of syntax you can in the MATLAB to get the solution of any particular you can say state variable. So particularly sol.x will be actually having the mess which has been decided by the solver, which consists of the time steps. Sol.y will be consisting of all the solution of yx approximated at the points which is in visible in sol.x, and sol.yp is also one of the variable which actually stores the derivative of the function y at the miss points which is in sol.x. So this is basically all the solution which is returned by the MATLAB DD solver. Okay. So for example, if you have this kind of delay differential equation, so you can create, and suppose that tau1 tau2 is this, and history function is y1t is equal to 1, y2t is equal to 1, and y3 is equal to 1, which is of course true for t less than equal to 0. Then you can create a function sample file which is called dd file by this one. So first define the lag variable which is z colon comma 1, z colon comma 2. So these are the lag variable, and with the lag variable you define the three-dimensional system as a this one. So y lag 1 1, that is this is basically y of y1 of t minus tau 1. Similarly, y lag 1 of 1 is y1 of t minus 1 plus y2 of t minus 2. So this will be y lag 2 of 2, and the third is y2, that is y2. So this is a function which defines the right hand side, and this is a function which defines the history function, and so you can call the solver by this technique, and you can solve the solution, obtain the solutions. So you can also use Mathematica. Mathematica is one of the symbolic software which is available for mathematical community. So in the Mathematica also there is a solver which is called ND-solve. You can use this one to solve the delay differential equation. So I'm not mentioning this one just because of paucity of time. So that's it all for my side. Thank you.
Sir, is there any more softwares to solve the equations?
For me, I know only two solver. One is your in MATLAB, another one is in Mathematica. But if you want, then you can always search. There are some actually package which is basically invented. For example, in Python also there are some tools which in Python also. There are some tools which is also available in C++ language too. But I have not used C++. I have used Python one. So there are some toolbox you can search on internet. You will find some package which is available for solution of delay differential equation in Python. Many times back, I used the solver which is in Fortran also. That is also very good solver, which is actually invented by the people which invented the solver DD23 in MATLAB. So the same person which they invented in MATLAB. They had already solved the delay differential equation in Fortran. So you can also use those packages.
Okay, thank you, sir.
Okay, so thank you.
Yes, yes, I am available. Okay. Is the presentation visible? My presentation is visible? Huh? Okay. Okay. Good afternoon, everybody. I am Dr. Fdp from Banaras Hindu University, Department of Mathematics. Now, my talk entitled is Visualization of Ricci flow. Okay. Now, the outline of the talk, first we have to introduce what is Ricci flow, and next the behavior of the Ricci flow solution of surface of revolution, and third one, the harmonic coordinate. The Ricci flow takes the form of a system of nonlinear heat equation for the components of the metric tensor. And last one is conclusion and references. Okay. Now, first, the introductory part, what is Ricci flow? Okay. So, before we go to start the definition of Ricci flow, you have to know what is a manifold and a Riemannian manifold, and then Ricci flow. You know that the manifold is a topological space. Okay. And you know that to find coordinate of a point in a topological space, we have to consider open set, okay, and with which is homeomorphic to Rn. That means a topological space is said to be topological manifold if it is locally Euclidean to Rn. Okay, locally Euclidean, that means if there is a point, there is an open set U, and corresponding there is an open set V in Rn, and the map from phi U to V is homeomorphic. Homeomorphic here in the sense bijective and bicontinuous. Okay, and this U comma phi is the chart. That is the chart or coordinate system. It is called coordinate system or chart. So to find a coordinate of a point in a topological space, so you have to consider a coordinate system, and this coordinate system is nothing but U comma phi. So what do you know? That means in graduation or class 12, the 3-dimensional coordinate system, 2-dimensional coordinate system. This also a coordinate system to define a point of the coordinate of a point in a topological space. Okay, and this collection of charts, if we take the collection of charts, we form atlas. Okay, so atlas is nothing but the smooth collection of charts. It is called smooth atlas. Smooth collection of chart here in the sense, if you take any two charts, they are CR compatible. Okay, now I am not going to details of that, but So, but we have to know the definition of a manifold. So manifold is a topological space which is homeomorphic to Rn and a smooth collection of smooth atlas in it. Okay, so that is the definition of a manifold. Okay, now what is Riemannian manifold? So Riemannian manifold, that means you have a smooth manifold which is Hausdorff's and second countable. You know that what is the definition of a Hausdorff space? It two distinct points corresponding up to two distinct open set milligam. Okay, disjoint. So that is it is true for any arbitrary 2 points on that space. That is called Hausdorff space. And second countable. Okay, that means has a fine countable basis. Okay, so smooth manifold with Hausdorff and second countable, and with also positive definite inner product on it. Positive definite inner product on tangent space of the manifold. It is called Riemannian manifold. That means M comma G is a Riemannian manifold. M, what is M? M is a smooth manifold, and G is called the Riemannian metric. Okay, it is a symmetric, bilinear, and positive definite. That means whatever the properties of the inner product, it also satisfies the properties of inner product. That's why it is called manifold with inner positive definite inner product is called a Riemannian manifold. Okay, so here G is not G it is called a Riemannian metric, which is defined tangents TPM cross TPM to R. Okay, okay. Now. So Riemannian manifold G it is not that is not include here in parameter, but when we introduce Ricci flow,
this slide is not moving actually. Slide is fixed in the third slide.
Yes.
Slide is not moving.
Yes, slide does not move because I give the definition. I want to yes, slide will move after my introductory part. Okay, okay. So before okay, so Ricci flow, that means here the definition of the Riemannian manifold. G is not a function of T, but when we introduce Ricci flow, G is the function of T. That means metric will be smoothly vary. Okay, so Ricci flow is mean by which one can take arbitrary Riemannian manifold and smooth out the geometry of that manifold. So what do we say? The definition of Riemannian manifold and this. So GT is smoothly varying. For the case of Ricci flow, smooth out the geometry of the manifold to make it look more symmetric. Okay, so Ricci flow can be defined for any dimension. Okay, here we restrict ourselves here to two-dimensional manifold as they are nothing but the easy to visualize that that is called the surface. Two-dimensional manifold is nothing but the surfaces. You know that they went on surfaces, the sphere, cylinder, planes, torus, and so forth. We know this when we study surface, there are two things about the surface. First one, extrinsic. Second one, intrinsic. What is extrinsic? Extrinsic is nothing but you can treat as a subset of a large set, as a subset of a large ambient space. In that case, three-dimensional Euclidean space. And intrinsic means by considering how the points in the surfaces stand in relation with each other, but not in relation in external space. Okay, so that is called the intrinsic. Okay, example. A good example of a surface is the surface of the Earth. Earth surface. Okay, and extrinsically, you know that it is a subset of R3. So intrinsic surface could, and extrinsically it is a subset of R3. Okay, but you can also view this surface two-dimensionally by using an atlas. And what is atlas? We already know. I have already told that what is atlas. Atlas is nothing but the collection of smooth charts. Okay. This way of thinking of a surface is not completely intrinsic. If you think by considering atlas, but it is not completely intrinsic because there is some more than one atlas that one could associate it to the surface. Okay, that means if a surface given, then you can define another way atlas. Okay, so that's why it is not unique. Okay, but they may be different in various minor way. For instance, in one atlas, the city of, if we consider Los Angeles, might be on the boundary of one charts, whereas in another atlas, it might be in the interior of any chart that it appears in. Okay. However, there are many facts one can deduce from atlas, which do not depend on the choice of atlas. For instance, using any accurate atlas of the Earth, one can see that one cannot travel from Los Angeles to Sydney without crossing at least one ocean. Okay, that is a real fact. You cannot cross without crossing at least one ocean. In fact, regarding a surface, does not depend on which atlas one use. So that is the fact. We say that it is intrinsic or coordinate independent It will run out that Ricci flow is an intrinsic flow on surfaces. Okay, it can be defined without any knowledge of charts or an extrinsic ambient pace. So that is the main basic thing. Okay, the Riemann surface or Riemannian surface or two-dimensional Riemannian manifold, or you can say this is surface M with additional object. You can say a Riemannian metric which specifies the distance dxy. You know that when we define metric on the Riemann surface or Riemannian manifold, we use Riemannian metric to define the distance, okay, between any 2 points x and y on the surface. The geometry of Riemann surface has to be very close to the geometry of Euclidean plane at the small length scales. Okay. Example for what the above statement means. Example, if you consider a Euclidean plane, it's a circle, it has area pi r square. Okay, but if we consider that circle on the surface, it has area. If the radius is very close, radius is very small, okay, then the area of that circle or disc, it's not a circle, it's a disc on that surface, is pi r square. So small scale, small length scales, you know, small length scale. That means if r tends to very close, r tends to very it's very small, then the area of the disc become close to pi r square. Or more precisely, we require that the ratio between the area and the pi r square converge to 1 in the limit r tends to 0. Okay, so next that is what is scalar curvature. Scalar curvature, now for the sphere, if we consider the sphere, the area of the disc bxr of a small disc bxr is actually little bit smaller than pi r square. Okay, when this is the case, we say that surface has positive scalar curvature at x. Okay, then you can say that the positive scalar curvature at the point x on that surface. On other senses, such and saddle, the area of the disc is bit larger than pi r square, then we say that the surface has negative scalar curvature at x. Okay, when they are same, we say that vanishing scalar curvature at x. Example is सिलेंडर में आप कोई भी पॉइंट ले लीजिए, उसका corresponding जो डिस्क होगा तो उसका जो आपका एरिया होगा एंड पाई आर स्क्वायर के बराबर हो जाएगा. Okay, so here we actually here we give the concept of positive scalar curvature and negative scalar curvature. What is that actually? Okay, and that is the definition or defined in this way. Rx equal, that is the scalar curvature. Rx is defined in this way. Next, that is Ricci curvature. What is Ricci curvature? Ricci curvature, where just consider two-dimensional plane, and that is our circle, and okay, and ax r theta v is nothing but the directional vector. In which direction you consider, that is in direction v, and it's make an angle theta. Okay, and the radius is r, and the point is x. So it is called ax r theta v. So inside a small disc, of a smaller angular aperture, okay, may centered around the small direction, some direction v, a unit vector from x. In Euclidean space, that area is nothing but half theta r square. You know that the area is nothing but half theta r square, sectoral area. But on the surface, the area might be slightly less than this. And in these cases, we say that the surface has positive Ricci curvature at x in the direction v. Okay, so we say, so what happened? That case happened. We say that positive Ricci curvature at point x. Okay, and another sense it is the negative Ricci curvature. Okay, and this is the formula to calculate the Ricci curvature. So in particular, the direction v in fact plays no role in Ricci curvature in 2 dimensions. There is no v. Okay. However, it is possible to extend it all the above concept to other dimensions. In higher dimension, it turns out the Ricci curvature is more complicated than the scalar curvature. For instance, in 3 dimension, it is possible for a point ax to have positive Ricci curvature in one direction and negative Ricci curvature in another direction. Okay, so now Ricci flow. Now we describe Ricci flow informally as the process. What is the process? Process is that stretching the metric G in direction of negative Ricci curvature and contracting the metric in direction of positive Ricci curvature. Okay, so that's the main thing. Okay. What is Ricci flow? Ricci flow informally process the stretching the metric in direction of negative Ricci curvature and contracting the metric direction of positive Ricci curvature. The stronger the curvature and the faster the stretching or the contracting of the metric. Okay, so then what happened? Actually, curvature को stronger करते हैं, stronger the curvature. Okay. The concept of stretching and contracting will increase or decrease the distance between the points, okay, of course, along this direction. And by changing the notion of distance, one also affect the notion of angle and volume. Obviously, if distance altered, then angle will be altered and volume be change hoga. Okay. So Ricci flow, that is the formal definition of a Ricci flow. Hamilton published a groundbreaking paper, 3 manifolds with positive Ricci curvature, Journal of Differential Geometry in 1982, introducing the concept of Ricci flow. And you have if you have a Riemannian manifold with metric G0 हमारा जो है first मतलब जो है t equal to 0 point पे जो metric है, the Ricci flow is a PDE, partial मतलब जो है PDE. That involves a metric tensor, that is the del G del T is nothing but minus 2 Ricci. It's a function of GT, and G of 0 at the time it is denoted G0, that is the boundary condition, okay, initial condition, where Ricci denotes the Ricci curvature of the metric GT. Now the behavior of Ricci flow solution of surface of revolution. Here in this section we actually visualize what happened if we study Ricci flow in the surface of revolution and what the geometry will convert to a symmetric form. Okay, so first here we consider a simple curve, plane curve, gamma phi a phi comma b phi in the xz plane of R3. We just consider xz plane and we consider a curve on that plane of R3. Okay. And it is a regular curve. That means gamma dot phi is not equal to 0 for all phi belongs to I. Okay, and here A is greater than 0 on the interior, and A is equals to 0 at the possible endpoints of I. That means A equal to 0. That means is the figure here. Here A is 0. Here A is 0. Okay, so and you know that the A that is the xz plane if we consider. So. That's the A, that's x-axis बराबर A and z-axis बराबर B. Okay, so yes, A phi comma B phi. Let A subset of R3 be a surface of revolution. That means what we actually a curve, that curve will revolve about the z-axis, and you know that you get a surface. You get a surface. You know? When you in a curve revolve about an axis, you get a surface. And this is nothing but surface of revolution. Okay, so obtained by revolving the image of the curve gamma about z-axis, and the local parameterization of S. So what will be the parameterization of the surface? This is nothing but the parameterization. You know that there is the circle, and that is the height. So you get a surface. That is the you have a circle का जो parameterization है, that is r cos theta comma r sin theta. Here r is nothing but a phi, and that the height is nothing but b phi. So that's the parameterization of the surface, and it's dependent on phi comma theta, phi and theta. and that is the domain phi 1 comma phi 2 and theta 1 comma theta 2. Okay, so and phi and theta be the standard coordinate on the surface of revolution. Obviously, surface of revolution naturally extend to a smooth manifold, and you know that it is a smooth manifold. It is a smooth manifold. Okay, so okay, so that is our surface of revolution, and that is our domain. And you know that that's the mapping. That's the mapping. जो parameterization rho. Okay, so here if we take a point on that surface of revolution, so rho is nothing but rho is the function of phi and theta. So the pullback metric of R3, pullback metric, that is our R3, and this is the subset of R3. S is nothing but our surface. So S is the subset of R3, and the metric on R3 is G bar. Okay, and the pullback of the metric is nothing but the metric on that space. Okay, so that's why it is denoted by rho star G bar. And you know that it's a homeomorphic. It's R2. It is R2. Okay, it is R2, and at surface is nothing but the homeomorphic to R2. So the metric. This metric is nothing but the metric on that surface of revolution. That surface of revolution that is restricted on S. G bar that is restricted on S. Okay. So we have to find out the metric on that R2 using the help of rho. So if we consider this is rho 1, that is rho 2, and rho 3. And you know that the metric on R3 is nothing but dx square plus dy square plus dz square, मतलब d rho 1 square plus d rho 2 square plus d rho 3 square. That is the metric. And now using the chain rule, d rho can be written as it is the function of phi and theta. So by chain rule, you get this. Similarly, by chain rule, you get that. Similarly, by chain rule, you get that. Okay, you get that. And rho 1, rho 2, d3, this is nothing but rho 1, this is nothing but rho 2, this is nothing but rho 3. Then after calculation, just put the value, you get this is in the form. So rho star G bar, that is the rho star G bar, that is the pullback metric on R2. This is nothing but that. So you can locally write what will be the metric on the surface of revolution. G bar restricted on S is nothing but it is a function of phi. So h phi d phi square. This is the d phi square. And a square, and that is nothing but a is also nothing but the function of phi. You know that a is nothing but function of phi. So that is you can write m phi d theta square with h and m yet to be determined. Now you have to determine h phi and m phi. Okay. Note h and m are independent of theta. There is no theta. So it is independent of theta. For our convenience, we will interpret theta and phi and theta as the standard coordinate on the Riemannian manifold V G star V rho star G bar, and consider the metric. This is our metric h phi 0 0 m phi. So if you write this metric in matrix form, that is nothing but that. Okay, and now if we compare this metric with that, then this equals to that and this equals to that. So a phi is nothing but that, and dv d phi, you just calculate dv d phi is nothing but that. So just integrate. So this is you get that. Now in particular, if you take example, consider g is nothing but 1 0 0 sin square phi. So in particular, you just consider particular case. Then what happened? 1 0 0 sin square phi. Then after calculation, a phi is nothing but sin phi, and b phi is nothing but cos c minus cos phi. If we put c equal to 0, then b phi is 1 minus cos phi, and c equal to pi by 2, so minus cos phi. And this is nothing but kya? It is nothing but the metric on S2. S2 that means sphere. S2 that means sphere. Sphere is here is the dimension of 2. That's why it is called S2. Sphere ka dimension 2 hai. 3 nahi. In differential geometry. Okay. So before we determine the Ricci flow of S, we first extend M and H at the poles. Okay. So at the poles, that means yes, this is the pole. This is the pole. Okay. So we just consider the what is the condition for the case of pole. So you know that m pole में क्या है? M जो है that is our m. M pole मतलब phi pole में क्या है? Phi हमारा जो pole है यहाँ पे क्या है? It is a 0. Phi is 0, and यहाँ पे भी end point पे हमारा phi जो है 0 है. So that's why m phi pole is nothing but 0. Okay. And similarly, because thus is followed that a phi pole is equals to 0. Intuitively, m should tend to 0 as phi tends to phi pole, and theta is undefined at the poles. Similarly, since smoothness of the poles are demand, we also require this equals to that. How can we get? From that equation. Because phi pole is equals to 0. Okay, so you get this. Now, so it is our metric. And if we calculate the Christopher symbols, there is a formula to determine the Christopher symbols, and if we use this formula to calculate the Christopher symbols, then you can also calculate the Ricci curvature, Ricci 1, 1. This is the formula, and you just put then you get this, and Ricci 1 to Ricci 2 equals to 1 equals to 0, and Ricci 2 equals to that. Now these four equation can be written. Ricci 1, 1 equals to q by g22, and Ricci 2 equals to q by g1, 1, 1. By q is nothing but that. Okay, so this is because the object is rotationally symmetric. Okay, you know that the symmetric here in the sense geometrically, there is our z-axis. So this portion and this portion are the same thing. Okay, symmetric here in the sense. Okay, so okay. Next, now let us consider Ricci flow S with its induced matrix. So we know that a two-dimensional Riemann manifold Ricci flow solution GT is conformal to G0. Conformal here in the sense some scalar multiply of G0 for all t. Okay. Here the initial metric G bar S. So the Ricci flow initial value problem induced therefore a system of just 2 instead of 3 second order nonlinear PDE. Okay, so from that here exist only Ricci 1, 1 and Ricci 2, 2, and other 2 is 0. So therefore we get only 2 PDE, 2 partial differential equation with initial condition. Okay, so so 2 PDE. Yes. Moreover, we obtain the local solution ht, phi and mt, phi. Remains independent of local coordinate theta. Yeah, that is not dependent on theta due to the rotational symmetric. Since h and m are independent of local coordinate of theta, so we can just evidently consider a PD on the interior of I. Hence, let us consider the initial value problem. That is our differential equation. This is our differential equation. Okay, and you know that the Ricci 1, 1 and Ricci 2, 2 exist. So I just put ij equal to 1, 1 and ij equal to 2, 2. So if we put ij equals to 1, 1, so this is del g1, 1 del t equal to minus 2 Ricci 1, 1, and g1, 1 we just consider that is h. So not consider, actually g1, 1 is h. Yes, look this metric. So this is g1, 1 and this is g2, 2. Okay. So that's why we just put h. So del h del t, it can be written ht. So this is our ht, and minus 2 Ricci 1, 1 Ricci. So Ricci 1, 1 ka value put kijiyega, so you get that. Similarly, mt is that. So we get two differential equals to PDE, okay, with initial condition mt phi pole equal to 0 and this equals to 0. Now you have okay, so PDE with initial condition, that means you must have a unique solution. So the above system can be solved numerically. Okay, and you know that there is so many solutions, but you have to choose such solution which satisfy the boundary condition. Okay, which satisfy the boundary condition. So under establishment a numerical system stable program, also note that by solving it numerically, we use the fact that there exists a unique Ricci flow solution. By solving the system above, we need to choose A0 and M0 previously, because not all this define a surface of revolution. So there are so many you can choose H0 and M0, but you have to choose M0 and N0 such way that satisfy boundary condition and also form surface of revolution. Okay, so here we choose H0 phi is equal to 1 and M0 phi is equal to that. Okay, so this is our initial condition. Okay, so let this with this sufficiently small, the metric is inspired by the metric of the two sphere, and observe that H0 and M0 are chosen such that it satisfies the boundary condition this. Okay, Now is C3 or C5, this is the constant. If we put C3 equal to 0 and C5 equal to 0, so this is nothing but the sphere, that is a sphere ka jo boundary condition hoga. This is nothing but that. Okay. Now, if we put so this is the solution. If we put C3 and C5 equal to 0, the picture have been taken at equal time interval, del t equal to that, are drawn in the same scale. So this is our sphere. So if we apply Ricci flow, then this sphere is symmetric to more symmetric. Okay, this is the case, is symmetric to more symmetric. Okay, so Ricci flow actually, what does Ricci flow does that geometric surface or geometric properties are contracted and sinking, and it goes to more suitable figure, that means symmetric figure. Okay. Next example, if we consider C3 equals to that and C5 equals to that, then this manifold goes to the more symmetric cases, that is the sphere. Okay. Okay. And this is another cases when C3 equals to 0.7 and C5 equals to minus 0.15, then this picture goes to that. Okay. Yes, that is the visualization. What happened if we apply Ricci flow on a Riemannian manifold. Okay. Next, that is Ricci flow regarded as a heat equation. This is the definition of the local coordinates xi are called harmonic coordinate. If you know that the Laplacian xi is equal to 0, and if we put the formula, then we get that, and this is equals to that. This is the theorem where we use this theorem only statement. Okay, and this is another corollary. Given a point, कोई एक point ले लीजिए manifold में, there exists harmonic coordinate, defined in some neighborhood of that point. That's the corollary, and this is the proof. Okay, so Ricci flow regarded as a heat equation. By theorem above, there exists neighborhood V of P and function Ui such that this equals to 0 holds in V. Okay, and this is the lemma. The inharmonic coordinate Ricci tensor is given by that. This is the proof. The Ricci tensor is given by the local coordinate by minus 2 Ricci jk is nothing but that. That just put the formula. Okay, and then that is the simplification. We just know to go to the details proof of this theorem, but actually, yes, our aim is that you have to look that it can be written as a heat equation. So this is the calculation background. So yes, this can be written this. Okay, and you know that del G del T is nothing but minus 2 Ricci ij. So Ricci flow can be written in this form. Okay, and so yes, more precisely, this can be written that. And in harmonic coordinates, the Ricci flow takes of a system of nonlinear heat equation for the component of metric tensor. This is our result. Okay, and this is 2006, Perelman was first offered the Field Medal for his contribution, geometry and his revolution insight into the analytical and geometric structure of the Ricci flow, but he declined. Next, 2010, it was announced that he had made the criteria to receive the first Millennium Prize for resolution of the Poincare conjecture, but then again is also related anyway. So here we give these two things because the importance of the subject. Yes, so there are three main papers: Perelman conjecture, geometrization conjecture. Okay, and applications. There is so many applications: uniformization theorem, geometrization conjecture, solution of the Poincare conjecture, differential sphere theorem, and recent developments. The Ricci flow has been intensively studied since 1981. Some recent work has focused on the question of precisely how higher dimension Riemannian manifold to evolve under the Ricci flow, and in particular what types of parametric singularity may form. Okay, and these are the references. These are the references. Thank you. Okay, thank you, sir.
Very good evening, sir. Shall I start my screen sharing? Okay, sir. Okay. So, good evening, everyone. I am Dr. Sana Ejaz, Assistant Professor, Department of Mathematics, Haji Bandanawaz University from Kalburgi, Karnataka. So, is my voice audible, sir? Okay. So, today my topic is...
Sure.
Okay. So today my topic is graph theory and its application in various disciplines. So many of the non-mathematicians are also have joined the meeting. So graph theory is one of the major discipline in major subject, major specialization in mathematics field. And we all should know that graph theory has various applications in other disciplines as well apart from mathematics field. So it is a branch of mathematics that deals with the study of graphs. So we have learned, might be in the higher primary schools and higher educations, that what is the graph. Like we have the basic things of graphs. So what is exactly graph theory is? Graph theory is a mathematical structure which is used to model relationships between objects. It consists of vertices and edges. A graph is a pair of like set of vertices and also a set of edges. Graph theory has a wide range of applications in various fields, including computer science, social network, transportation, biology, and more. It provides a powerful framework for analyzing and solving problems related to connectivity, optimization, and data presentation. So here are some applications of graph theory that we can study in the further slides. Like I have shown here one of the image wherein we can easily make out where the graph theory applications are mainly used in other disciplines. Like it is being used in computer networks, electrical engineering, mathematics and OR, and other physics, chemistry, biology, social science, Google Maps, and its main important application is in computer sciences. So we can see that the major applications of graph theory is in transportation networks. Transportation networks, like when we see the delivery people of Zomato, Swiggy, and other transportation, wherein they use graph theory as the main tool to analyze the shortest path a can make from the hotel to the delivery residence. And we have the application in social networking sites, search engines and web graphs, supply chain and logistics, biological networks, computer science and technology, recommendation system, marketing and customer segmentation, network infrastructure, fraud detection, epidemics, and disease spread. So we all see this application in further slides. So the applications of graph theory in computer science and data science. Here in the computer science, where we can see the social networking sites. When a person is in social networking site like Facebook, Instagram, WhatsApp, and other many websites, many social networking sites like Snapchat and all, when we are in the Facebook for an example, so we get a suggestions of friends. Like when we have a friend list of 10 friends, then 10 friends have, they also have 10 friends in their contacts. So when we get the suggestions of other friend contacts, it means that there is a connectivity between our friends and their friends. So from those friends list, we get a suggestion. So here they are making a social networking graph from which we are able to connect each other. So this is very much useful in social networking site. It's been using since many years. Economic networks, biomedical networks, information networks, and other various networks. So graph theory used to represent and analyze a wide variety of network information and has numerous modern applications within data science. It has also been fundamental to the development of numerous foundational algorithms from Google PageRank to Netflix content recommendation. So yes, here also we get other websites, like other entertainment websites like Netflix and Disney Hotstar and so and so. So we get suggestions of movies or suggestions of something on our website. If we don't suggest, even if we don't search for it, we get those suggestions by how? We get those suggestions by graph theory networking system. So here in graphs also is helpful in data structure. Here we can see the different type of graphs, like pictograph, we can see histogram and flow chart and everything else. So these types of graphs are also used in many other fields still now. So now the applications of graph theory in computer networks. As how I told how the social networking modeling is being done in other social media sites. So graph theory aids in modeling social structures and analyzing dynamic interactions within social networks. So communication analysis. It is used to study communication patterns, information diffusion, and influence propagation in various communication networks. So here, communication networks, we can say that until recently, computer and network security has been formulated as a technical problem. However, it is now widely recognized that most security mechanisms cannot succeed without taking into account the user. A key area in security research is authentication, the determination of whether a user should be allowed access to a given system or resource. Alphanumerical passwords for authentication, they have also been used as security and usability problems. So this all will be helpful. Also, the graph theory has an applications in cloud computing as well. So cloud computing as well, we all might have aware of. Cloud computer plays a very important role in graph theory. So it is graph theory has an applications in cloud computing technology. It is this technology is an open standard, service-based, internet-centric, safe, convenient data storage and network computing services. So these type of services are provided by cloud computing with the help of graph theory. So here we can also see this web. It is represented by a direct graph. This is a type of a graph wherein we can see the vertices are directly connected to other vertices with the help of an edge. So these vertices are the web pages. So you can see here this are all the web pages. They are directly connected from page A to B and exits if only if A connects to the link B. So this is, you can see the graph network, how they have made with the help of vertices and edges. So the now next application, like you can easily see here how the social networking site is being connected to each other, how the friends are connected, how the relatives are connected to each other. And here also we get the friend suggestions, we get the relative suggestions on our social networking site. And here also all the networking has been done using the graph theory methods and tools. So here is one more very important graph theory in medical science. We can see that the graph theory has been majorly used in medical sciences. So you can see that analysis of human heart networks can be done using graph theory, graph representation of patient data, representing and curing diseases networks using graph databases. So you can see here the graph databases have been used to analyze the patient's disease. So graph-based visualization of sensitivity medical data. So non-invasive imaging like fMRI is used in brain imaging, wherein we can easily see that the spread of the diseases from where it has been spread and how much it has been spread in the brain. So this is a graph theory analysis using this fMRI technique and non-invasive imaging techniques. We can use, suspect the brain disease and its spread. So here is the network connection, how the nodes here we can see that the nodes are nothing but the cortical regions. Here is the structural brain network and edges, cortical thickness correlations, fiber connections. These are the methods what they use, DSI, DTI and transneuronal tracers. Functional connectivity can be done using the graph theory, fMRI, EEG, MEG, weighted versus binarized. So here the networking is being done with the help of nodes and edges. So here are the applications which are used in medical sciences like data processing, parcellation, then time course extraction is done, then graph theory analysis will be done, then functional brain network is done, then binarized connectivity and correlation matrix. So next, another important applications of graph theory is in data mining and public health. Graph theory is used for data mining in public health. It helps identifying patterns of deprivation and high-risk areas. Whereas the deprived areas in any other cities, in any other villages where the deprivation of data mining is done, we can make the patterns using the graph theory. And where is the high-risk areas also can be done using the graph theory. Network analysis of biological data sets. Graph theory is applied to analyze large-scale biological data sets. It helps shift the research focus from individual molecules to group of molecules. So analysis of motor activity in patients. It is also used to analyze motor activity in patients. It helps identify differences between diagnostic groups and normal controls and compare different algorithms for time series analysis. Graph theory is also used in molecular epidemiology to study the spread of diseases. It helps analyze traffic networks, navigable networks, and optimal routing for emergency response. Like how traffic network is being done using graph theory is like the signals where we have to put the signals, and one signal can cover how much area one signal can cover across it can be done using the graph theory technique. And navigable networks and optimal routing for emergency response. Also, one of the major important application of graph theory is also electrical e-graph. It has been recently, research paper has been published as e-graph. It is nothing but an electronic graph, wherein we can see that the towers of mobile towers has to install where the highest the range of the mobile tower, how much area it will cover across the city, and according to that particular technique we can minimize the number of mobile towers to be installed in the city. So this e-graph, with that method, with that technique, we can make use of the graph theory and we can install the minimum number of mobile towers across the city. So it also helps in installing the it's also help in mobile networking also. So consolidation of disparate data sources. Graph technology, which is based on graph theory, is useful when consolidating extremely large volumes of connected data sources. This is particularly relevant in healthcare, where disparate data sources need to be integrated. So graph theory is widely used in biological mathematics to model and analyze biological networks. It also helps in understanding various biological problems as well. So yes, one of the major application is also in Google Maps. Like how you can see here, there are 3 methods used in this Google Maps. Earlier, they used to use BFS, that is breadth focus, to start visualizing the shortest path and the position from where it started and where it has been covered the area. Then next is the Dijkstra algorithm technique. It also shows the shortest path or the nodes visited in search. So by this technique, we can see the how much area it's been covering and the places where we can visit. Next is the A-star algorithm. This is also the latest one. Dijkstra is the generalized form of BFS. It is a generalized form of BFS in which order of traverse nodes is not determined by number of edges from the source node, but the distance from the source is determined by this algorithm. So these 3 techniques, BFS was the earlier technique, Dijkstra algorithm is the latest one, A-star is also the latest one. So it is used to represent and analyze a wide variety of network information and has numerous applications in various domains. So here the Google map. So you can all see the image here, how the Google Maps has been drawn with the different colors. So it is also called as 5-color theory, 5-color problem or 4-color problem also. So the graph theory, Google Maps uses graph theory to model the road network. So here you can see the how the road network has been made. In graph theory, roads and intersections are represented as nodes and edges. So here we can see that one point to another point is nothing but an edge, and one point is the vertices. Here the road maps, road and its intersection has been represented. Algorithms such as Dijkstra's algorithm and A-star's search are used to find the shortest path between 2 locations on the maps. So when we are traveling to one place to another, we will be using Google Maps. So it is showing how the shortest path can be taken by a traveler. So these 2 algorithms have been used to find out the shortest path between 2 locations. So also the routing algorithm, how the routing algorithm actually works in graph theory. So discrete mathematics is essential for developing routing algorithm that help users find the most efficient route from one location to another. These algorithms take into account factors like distance, traffic conditions, and road closures to calculate optimal routes. So yes, you can even see when you are using the Google Maps while traveling to one place to another, from one place to another place, they will be having few options of your routes. If you are taking by walking distance, if you are using the car, if you are using the 2-wheeler vehicle. So every time whenever you're giving the option, it is showing a different path connection. It is showing the different route for you. Like when you are going by work, it will show the shortest path, how you have to take the shortest path. So all this routing algorithms can be done using this Dijkstra algorithm and A-star search. So you can see that there are different options given in Google Maps. If you want to avoid traffic conditions, if you want to avoid distance, if you want to take highways, if you want to take straight paths, everything, like if you want to have hotels in between, whatever the option you give, they will give you another solution for it. All such things happen using the routing algorithm method. This all happens by this 2 algorithm, Dijkstra algorithm and A-star search. So another is geographic information systems. Google Maps relies on GIS technology, which involves discrete mathematical concepts for representing and analyzing geographical data. So geographical data is very much required for the Google Maps to actually work or actually implement it. So to get the geographical data, so discrete mathematical concepts like GIS technology is being used to analyze the geography. So graph theory also has many applications in real world, like internet and web pages, social networks, transportation networks, supply chain management, computer networks, recommendation systems, biological networks, data visualization. So internet and web pages, where we can see that web page is a vertex and hyperlinks between pages and edges. This graph structure is used by search engine like Google to rank web pages based on the number and quality of incoming links. Like if you go on visiting an internet web page, you can see other web page also will give some suggestions or some shopping links. You will get something like whatever you like on other social media networks, they will pop up on your screen, like any if you want to buy this, if you want to buy that. So how does that come? So there will be hyperlink between those pages and the page which you are going to refer. So this all happens because of the networking systems. So social networks, like how I have earlier told, how the social media platforms like Facebook, Twitter, LinkedIn utilize graph theory to model and analyze social connections between individuals. Graphs help identify relationships, communities, and influencers within the network. Like for an example, if you are on an Instagram, if you follow a celebrity, if you follow that celebrity, then the connected link of those social celebrity, you will get in the suggestion box, like if you want to follow that particular person also. And then if you're visiting, if you're going on to the if you're watching other videos or other shorts, like, so when you like any of the page, then that kind of suggestions also come in the in your suggestion list. So all this happens through a social networking sites. Then transportation networks. Graph theory is used to model transportation networks such as road networks, airline routes, and subway system. Yes, road networks and airline routes and subway systems. Airline route is also very important. The flight which one flight is going at this time, another flight is going on another time. They are all connected to each other. Like one country and another country, flights are all connected to each other. They should, like one city and another city, airports are all connected. So that there should not be overlap of the time and there should be no air trafficking. So that's why a transportation networking has been followed. Also the road networks follow the same system, and also the subway systems. So these graph algorithms help optimize routes, plan schedules, and analyze traffic flow. So this is also very important part in the networking systems. Then supply chain management. Graph theory is applied in supply chain management to optimize logistics and distribution networks. It helps determine the most efficient routes for transporting goods, minimizing cost, and improving delivery times. Computer networks. Graph theory is used to analyze and design computer networks, including the internet, LANs, and wireless networks. Help optimize network performance, routing, and fault tolerance. Then recommendation system. Many recommendation systems, such as those used by e-commerce platforms and streaming services, utilize graph theory to suggest products, movies, or music based on user preferences and connections between items. Yes, as I told earlier, that those suggestions of the products which you like on another website will pop up on your screen. The movies which you like, or the shorts which you see from other website, that also will be in your suggestion box, because they are all, the networking sites are all interconnected to each other. Then biological networks. In graph theory, used to model and analyze biological networks such as protein interaction networks, gene regulatory networks, and neural networks. It will help understand complex biological processes and identify key components. Like biological networks, what are these biological networks? So as we have gone through the COVID period, when the COVID period has happened, we can say that a person who is having a COVID has the high susceptibility of spreading the disease among the among the family members, among the person who are in his contact. So here the connection of one person to other person to other person, like they all are interconnected. So this connection of biological networks can be done by graph theory, and the person who has been suspected with the disease has to be quarantined so that the spread should not happen. So all this biological complex biological process has been done through the graph theory techniques. Data visualization. Graph theory is employed in data visualization to represent complex data relationships and dependencies. Graphs can reveal patterns, clusters, and trends in the data, aiding in decision making and analyzing. So these are the few important books of graph theory where we can use them to study about the graph theory and its applications. So other important graph theory applications are in data mining, image segmentation, clustering, and image capturing. And one of the important application I have given in my thesis book, wherein we can use the graph theory technique to find out the susceptibility of spread of the diseases and how we can stop the spread of it to other person who are in contact. So thank you, everyone. This was my presentation. Okay, sir.
Okay, so good afternoon all. Just let me share my screen and then I can talk. So am I audible properly to all of you? Okay, just few seconds you give me. Okay, so I hope that my screen is clearly visible to all of you. Okay. Okay, so how much time I can take? 40 minutes, fine. Thank you. Thank you. So then let us start. So today I was thinking to discuss about little bit how mathematical things are useful in fluid dynamics. So many people maybe heard about that methods in a easier way to understand complex flow system. So first, I want to give a brief introduction. So let us start with the brief introduction. That is, we are basically interested in hydrodynamic stability theory. So what is that? And how we can check stability of a system. So I have given two basic example here. So if you start with our daily life example, like tap water. Okay, this is first figure. If you see, this is tap water. So in this figure, I have given P part like A, B, and C. So if you see part A, then it is when you are opening your tap at the beginning, when you are slowly opening your tap, then how water is coming out from the tap. And then middle one, after certain time, if you are increasing the force of the water in your tap, then that is B part. And then if you are fully opening the tap and pressure is high, then what happening? That is given in figure C. So these three states, every day we are seeing what are they? Actually, first one, this stage is known as equilibrium stage or laminar state. Okay, where your streamlines inside the flow are organized, somewhat locally parallel. And then next one, this is called patterned flow. That means there is some disturbance, some extra pressure is there. Due to that, flow system is disturbed. And last one, it is chaotic or turbulent kind of flow. Fine. So in this case, if 3 stage of a flow system, if you study, then from the pattern state, you can either go back to the equilibrium stage or you can go to the turbulent stage. So this perturbation stage, that means there is some disturbance that is very important. Depending on the disturbance or high pressure, if you are going to turbulent stage, then your system is unstable. If you are going back to earlier stage or equilibrium stage, then it is stable. This is the basic idea of hydrodynamic stability theory. Now, how to check this stability? To check the stability, you have to check that at every stage, if you are giving some perturbation, then that perturbation is growing or decaying with respect to time and space. That is the only condition you have to check. Now, where we can see such kind of instability, hydrodynamic instability. So in many natural example and industrial example, actually you can see this hydrodynamic instability problems. But one of the example here I have given, that is blood flow inside human body or any animal. Okay. So inside human body, that blood flow system, you know that blood flow system has some pressure, and this hydrodynamic instability can happen inside your human body, and it can have a bad impact in your in the human body, and that is nothing but your heart attack. If hydrodynamic instability of the blood flow system is high enough, then heart attack can happen. And another example I can tell you that how this hydrodynamic instability can give you a good impact in your real life system. If you are injecting some drug somewhere inside in the body, and it is actually going from one place to another place wherever it is needed, that also a result of hydrodynamic stability, and in that case it has a good impact. Okay, so I hope that I could explain that what is the basic idea of hydrodynamic stability theory. Now we can move towards little bit complex problem. So complexity inside flow system can occur in many ways. So it can occur due to property change inside the system, or it can be due to the geometry of the system, or due to presence of some different kind of species inside the system. Again, I have given 2 examples here. One is from industrial background. So that is primary cementing. In chemical industry, actually, we can see such kind of things. And another one is our tear film. Okay, tear film is very thin. Okay, but still inside tear film, it is some micron. But still inside tear film, there are different layers. And due to coexistence of different layers, it is a very complex flow. Okay, so study of tear film or some chemical industry problem is very important. Now, with this idea, if we move towards some more discussion, so we are interested in complex flow problems here, and that complexity we can simplify in terms of mathematics. So how we can describe those complexity inside a flow system? Inside the flow system, if we are considering stratified flow, that means flow property changing from one place to another place inside the flow system, then that is called stratified flows. And in the case of stratified flows, let us understand mathematically how actually flow configuration can be different from one problem to another flow. Here I have given 3 figures, figure 1, figure 2, figure 3. Inside a channel, just a simple geometry. You have 2 boundaries, a upper wall and lower wall, and inside that there is some flow system. And I want to classify stratified flows or complex flows in different groups. So first one, if you see, there are 2 different fluids, fluid 1 and fluid 2, and their properties are different. I have considered one property, and that I have given in using this line, that step kind of function. So in fluid layer 1, it has one kind of behavior. In fluid layer 2, it has one kind of behavior. So we have a step kind of function. So here we have used step function to describe the property of the problem. Now, if you move to second example, then here you say that property either varying continuously from lower wall to upper wall, or as a linear function, or as a non-linear function. Okay, this kind of situation can occur. And third one, if say between two different fluid, there is another fluid which is the mixture of fluid 1 or fluid 2. In that case, what will happen? Your fluid property can vary still continuously from lower wall to upper wall, but there is a constant value in the lower wall, and there is a constant value in the upper wall, and there is a smooth variation in between those layers. And this kind of problems are known as actually mixed layer problem. So this is, or a smoothly stratified problem. Okay, it has a diffusive layer between two fluids. So such kind of three different kind of stratified or complex flow we can find out in channel kind of geometry. Okay, so next let us understand what is stability, instability, naturally stable or conditionally stable things. So when we are talking stable, so if you see figure 1 again, then stability means say there is a ball in this region. So there is a curve or say some place, you kept a ball. If you give a small disturbance to this ball, then what will happen? It will move from its place little bit, but a small disturbance will not give it enough moment to go away from this place. Okay, so this kind of situation is known as stable situation. However, if you see the second figure, then here again, if you give a small perturbation to or disturbance to the ball, then what will happen? This ball will go away from this place and it will never come back to this place. So this is called unstable situation. Now, third case, if you see, this is neutrally stable situation, because if you give some disturbance to the ball, it can move from one place to another place, but it cannot go completely away from this place. Okay, this is called neutrally stable. And last one, it is known as conditionally stable situation. Here, if you give small disturbance, then that ball will be in a stable position. It will move like that and again come back to this position. But if you give enough strong force to this ball, then it will go away from this region. So it will go somewhere else. So this kind of situation is known as conditionally stable. Okay, now let us understand the mathematics behind this kind of problem. So as I told at the beginning, we want to discuss the application of dynamical system. So to describe this kind of problem, first we have to consider one dynamical system which is given here. So it is dq by dt equals to fq, re, where re is a parameter. Okay, just control parameter, nothing else. So such kind of dynamical system, if we consider here, either it can be a single equation or it can be multiple equation based on your problem. Okay, so if we have such kind of equation, differential equation to describe this problem, then you know that depending on the behavior of the function fx or fq in the right hand side, it can be linear, it can be non-linear, because I have given a general function f of q comma r, where r is a control parameter only, and q is the property which is changing. Right? So now, if say this is a non-linear problem or linear problem, whatever, if say it is non-linear problem, then what will happen? We can linearize it and solve it in the case of dynamical system. If it is linear system, then directly we can solve it. And in the case of dynamical system, it is very important first to find out some equilibrium solution. So to find out the equilibrium solution first, what we have to do, the time rate of change is 0. So which is given here. And this tells us the solution, equilibrium solution of this dynamical system can be given by f of uv comma re equals to 0. So if we solve this equation, then then you can get the solution QB. So QB is known as equilibrium solution at the equilibrium point. And equilibrium point is given by the condition dQV by dt equals to 0. Now, in below, again, I have given the behavior of the solution depending on the control parameter. The role of the control parameter is nothing but it will give you the region where this system will be stable, unstable, etc. It will give you some extra information about the problem and extra grip on the problem, nothing else. Okay, so next, as I told, we have a system that is given by the dynamical system. Now, next what we have to do, we can give certain disturbance to that system. Okay, and we have to understand that disturbance is growing or decaying with respect to time, space, etc. to understand the stability. So here I have taken Q, the general variable Q as QB plus small q, where Q is the perturbation. So this perturbation quantity, we have to check the behavior of the perturbation quantity Q. So if we substitute all these things, this new variable QB plus Q in our governing equation, dynamical system, and if we use the equilibrium condition in the equation, after simplification, we can end up with equation 1, which is d small q by dt equals to j into q. So this is very simple dynamical system behavior, and in that case what we can get one matrix which is known as Jacobian matrix given by J. So Jacobian matrix, once you know, then you can study the behavior of this dynamical system, and after knowing the behavior of this dynamical system you can easily explain the behavior of the perturbation. And so this Jacobian matrix, how it is, that is given here. These are nothing but, these are each component are nothing but some partial derivative of the function f. And you know, this kind of dynamical system has actually some particular type of solution. So if say this is autonomous dynamical system, then the solution can be given as q bar into e power of lambda t. Okay, what is lambda? Lambda is the eigenvalue of the system. That means if you know the eigenvalues and eigenvector of the matrix, Jacobian matrix J, then you can easily write down the solution of this system 1, which is given by qt equals to q bar into e power of lambda t. Fine? Lambda are eigenvalue. Fine? And depending on the behavior of the lambda, we can conclude about the stability, instability, etc. of this system. Right? So this lambda eigenvalue, how to find out this lambda eigenvalue? To find out that, we can substitute this whole thing in equation 1 and we can find out an eigenvalue problem. Lambda q bar equals to j q bar. So j is the Jacobian matrix, lambda is the eigenvalue, and q bar is the eigenvector of this system. Once you find out all the eigenvalues and eigenvector of the matrix J, then you know the behavior of the solution, and you can give the idea about the stability of the perturbation quantity Q. Fine? Okay, fine. That was a ordinary differential equation. So we took one ordinary differential equation in terms of dynamical system, and we saw that how this theory works. Now, similarly, if you have a, say, one-dimensional wave equation, then it is a partial differential equation. So in this case also, similar way, you can construct a eigenvalue problem. So here you have to consider the trial solution first, and after using that trial solution, again you can get some eigenvalue problem, and that eigenvalues are nothing but that omega n, and eigenfunctions are un bar. Okay, so therefore this theory is applicable for ordinary differential equation as well as partial differential equation. Suitably, if you can implement this, then easily you can find out the solution and the behavior of the perturbation. So here I am not discussing this one in details because this will be similar like your earlier case. Like ordinary differential equation case, you can implement here and you can find out the eigenvalues and eigenfunctions. Now, again, if we come back to the complex flow problem again, then this perturbations or disturbance, as I told, it will dependent on time and space. With respect to time and space, you have to check that what happening to the perturbations. And when we are giving perturbation, we can think that perturbations are wave-like. it is certain kind of wave, and that is quite obvious. You know that if you throw a stone in a pond, or if you give a disturbance in a glass of water, then on the top of the pond or on the top of the glass of water, you can see certain waves, and those are the perturbation waves or disturbances. Fine. So same thing I have given here, and you can see those disturbances can grow with respect to time, or with respect to space, or with respect to both. Depending on the behavior, you can tell that it is temporal or spatial or spatiotemporal. So this thing has been given here. So in first two cases, if you see, so initial wave is like this, first figure, and second figure you can see initial wave has a higher amplitude. Okay, so with respect to time, there is an increase. Okay. But if you see last two figure, then here spatial increment is there. So this is the initial position, and then with respect to time and space, this is the final position. So spatial growth is there. Okay. So therefore, a disturbance or wave can grow with respect to time, or with respect to space, or with respect to both. Fine. So if we compare now this our complex flow problem, the examples whatever we have discussed till now as an ordinary differential equation or partial differential equation, what we did, actually we had an equilibrium solution, and then we gave some disturbance, and we add both the things to get the ultimate solution. So same thing here, say we want to find out U, which is a solution of a complex flow problem. Then first we have to find out the equilibrium solution in terms of U bar, and then add some perturbations to that, find out that perturbation amount, and that will give you the general solution. So graphically, same thing I have given here. This is the perturbation, and this is the mean flow or equilibrium solution. So this one U bar, and this is perturbation, and so we have U, which is, this is general solution. So capital U is the general solution, which is the sum of your equilibrium solution plus the perturbations. Okay. So next thing, in the case of complex flow problem, if you want to convert, say you have a complex, very complex geometry or complex system, and you want to convert that system from the partial differential equation to ordinary differential equation, because you know a system of coupled partial differential equation is not easy to solve. And most of the natural problem or complex flow problems, they contains a set of partial differential equation. So in that case, our aim should be try to convert those partial differential equation to ordinary differential equation in such a way that you can easily solve it. Okay. So to do that, you can take help of Fourier series analysis. So you know that a wave, a general wave or perturbation can be written as sum of different type of waves. So each waves are one Fourier modes. Okay, so like zeroth order, first order mode, and higher order mode, if you consider, then a general wave can be expressed as a combination of all those modes, Fourier modes. So we can take help of Fourier transformation as well as Laplace transformation together to convert complex flow system problem from PDE to ODE. So that thing we have done here. And that process is known as normal mode analysis. So in the case of normal mode analysis, you are actually using Fourier transformation and Laplace transformation together to convert the PDEs to ODEs. Fine. So here, the form of the solution is given in point 2. So your normal mode solution has, usually the normal mode solution has two parts. One is wave part, which is exponential, which has exponential dependent, and another is just amplitude. Okay, so phi y. So I have taken a general solution like phi y into e power of something. Now, if you see e power part, normal mode solution part, then e power part is dependent on x and t. But in front of x, there is some coefficients or parameter. So that is sometimes negative and sometimes positive. So depending on these parameters, therefore, we can actually name our stability problems. Okay, so in this normal mode analysis, we have two things. First one, the wave number of the perturbation waves and the frequency of the perturbation wave. So wave number is given by alpha and frequency is given by Q. Okay, so now if alpha is real and omega is complex, in that case, the stability analysis will be temporal, because in this form, in this general form, if you put that alpha real, then there is no dependent of this perturbation with respect to space, only dependence on the time. And depending on the omega I parameter, because it is multiplied with time t, so depending on omega I parameter, you can judge the stability or instability. So which is given in the last point. So for some real alpha, the system will be stable or unstable if imaginary omega, which is the frequency, given by omega I is less than 0, then this solution will not increase or it will not grow with respect to time, because omega I less than 0 means time into some negative quantity. So this exponential part will decay. But if omega I greater than 0, in that case, this exponential part will grow with respect to time, because time is multiplied by a positive quantity and it is an exponential function. Fine. So in that case, it will increase with respect to time. And if omega I equals to 0, then no change will happen. It will remain as it is. So these three situations are known as stable, unstable, and neutrally stable situation. Here again, I have given some set of geometries, simple geometries. So your flow system, like capital Uy, which is the solution of your flow system, can have different kind of behavior. It can be a parabolic function, it can be some hyperbolic function, it can be some say x cube type function, some sine function, cosine function, any kind of function can be this capital Uy. Okay. However, depending on the behavior of the solution, your stability behavior will change. So here I have given such class of example of Uy. So Uy can be any kind of function, and depending on the behavior of Uy, your stability behavior will change. Okay. Now, finally, actually, I want to enter in that complex flow problem, where we have a set of governing equations, and I want to apply this theory, whatever I have discussed till now. Okay. So if we consider a simple geometry problem, then you know every flow system can be described using Navier-Stokes equations. So here I have given that only. You have a continuity equation and 2D problem I have considered. So you have a continuity equation, then x directional momentum equation and y directional momentum equation. So a continuity equation is nothing but the mass conservation law it will follow, and remaining two momentum equation will follow momentum conservation. So these are known together as Navier-Stokes equation. And since we are solving certain particular problems, so we need certain boundary conditions. So depending on your problem, your boundary condition can be no slip condition. That means at the boundaries there is no velocity, or it can be some slip condition, or it can be symmetric condition. If say your problem is symmetric about some line or some space, then it will be symmetric condition. Or if say instead of both side wall, if you have a free boundary at the top of your problem, say like water in pond, water in river, water in a glass, so it has a free surface. Top surface is not closed. So in that case, you have to use free surface boundary condition, and that includes kinematic condition as well as stress balance condition. Okay, so to mathematically formulate the problem, you have to use certain equations as well as boundary conditions that are given here. Now again, you have to find out the equilibrium solution of the problem, like same like our example that ODE which we have solved. Similar, like you have to find out your UB first. To find out the equilibrium solution, your time derivative you put 0 and then you solve it. So we could get one equation like this from the Navier-Stokes equation, simple equation we got in the equilibrium state. So in the equilibrium flow, your Navier-Stokes equation gives you this simple equation with simple boundary conditions. Right? So if you solve those this system, then you are getting uby equals to y square minus 1. So this kind of flow is known as Poiseuille flow. So depending on the boundary condition at the boundary, we could get this solution. And this is the equilibrium solution of the Poiseuille flow. But this is not the general solution. Now, to obtain the general solution small u, you can add the perturbations. Okay, and then substitute everything in your Navier-Stokes equation, which is given earlier in equation 1. Substitute and then simplify it. So after simplification, you can see we could get equation 2, 3, and 4. Equation 2 is from continuity equation, 3 and 4 from the momentum equation, from the earlier, just the earlier slide. Okay, and certain boundary conditions, which is given here. Okay. Now, as I told, you can linearize it. You can linearize the system. Equation 3 and 4, they are non-linear because there are terms like u cap into u cap x, v cap into v cap y. So these are perturbation quantity. So with respect to perturbation quantity, there are certain non-linear terms here because multiplication between these various perturbation quantities, you can see these yellow marked terms. So they are non-linear terms. If you say that these are not since they are perturbation, small quantity, so their multiplication will be small. And so we can omit these terms because their multiplication has very small contribution in this equation. So you can omit these terms to simplify. And after simplification, you can get this equation 5, 6, 7. So these equations are perturbation equation. Perturbation for the perturbation, this equation you can get after ignoring the nonlinear terms. Okay. Next, from these equations, we have to use the normal mode solution like Fourier transformation and Laplace transformation to convert this partial differential equation to the ordinary differential equation. So equation 8 is the final stability equation of the complex flow system, which we got from the system of partial differential equation, which are none other than Navier-Stokes equation. Okay, so equation 8 is completely ordinary differential equation, and now it is easy to solve. However, inside this ordinary differential equation 8, there are certain unknown parameters like alpha, which is wave number, and c or alpha into c, which is omega, which is frequency. So alpha and omega, those are unknowns. Now, to solve this problem, you can assign certain wave numbers and find out the frequency. So this is finally this ordinary differential equation 8. It is nothing but a eigenvalue problem. It is a ordinary differential equation of 4th order, and it is a eigenvalue problem. So finally, we reach to, again, we have to solve the eigenvalue problem. Now, since this eigenvalue problem is complicated one, it is not like that our example which we have discussed as a simple dynamical system. It is not like that. It is a 4th order equation. So directly you cannot solve. You have to apply certain analytical approach or numerical approach. So here, analytical approach are sometimes not that much useful because if you have a complex geometry, complex system, you cannot handle with analytical approaches. You have to go with numerical schemes or numerical methods. So here I have given few methods, like you can use finite difference or RK method, spectral method, and shooting method. But most convenient method and accurate method for this kind of problem is Chebyshev spectral collocation method. What is this method? You have to discretize your domain. In which domain you have to solve this problem? You have to discretize the domain, and then in that domain you satisfy your equation. You use the Chebyshev polynomials to approximate your solution and satisfy your all equations and boundary conditions in each point of the discretized domain. So discretizing points are nothing but Chebyshev collocation points. So after satisfying the equation and boundary condition in each point, you will end up with a matrix equation, which is nothing but AX equals to C into PX. You have seen in many places eigenvalue problem, but this is little bit different. You know how to define the eigenvalue of a matrix. It is AX equals to lambda x. But this system is not like that. It is AX equals to C into BX, where A and B are two different matrices. Fine? And this is known as generalized eigenvalue problem. So here C is the eigenvalue. X, capital X, is the eigenfunction of the system. A and B are coefficient matrix. So this kind of system is known as generalized eigenvalue problem. This is not the regular eigenvalue problem. Regular eigenvalue problem is like that, AX equals to lambda x. Fine. So this system, now once you get this system of equation, eigenvalue problem, you can solve it. You can use MATLAB or any other software to solve it, or you can find out the eigenvalue C in other way. Right? But after getting, so I am not discussing this Chebyshev functions and Chebyshev collocation method in details because it will take time. So at least you know that this Chebyshev collocation method use the Chebyshev polynomials and points and certain properties of Chebyshev polynomials. If you want to know more details, you can just Google it. So these are nothing but this discretization process, etc. I have discussed about the Chebyshev collocation method. And after that only we got that matrix eigenvalue problem, AX equals to C into BX. So finally, if we solve this, we can get some eigenvalues, as I told. So we can get some eigenvalues, and if you plot those eigenvalues, here the first figure, it is the plot of eigenvalues. Then what will happen? If your eigenvalue, any eigenvalue has positive growth, means it is more than 0. If Ci is positive, then what will happen? Your system will become unstable corresponding to that eigenvalue. So you have to identify those eigenvalues which has positive growth. Fine? And those are known as unstable eigenvalues. But if no such eigenvalue exists, then it will be stable situation. The corresponding eigenfunction of the problem, this complex flow problem, is given here in figure 3 and 4. Thus, just the behavior of the eigenfunction, how they are changing. Depending on these behaviors also, you can conclude that it is stable or unstable. Okay. So some other results I have given here. So depending on actually behavior of this curve, if say curves, these are growth rate curves. If growth rate curves is passing 0 line and it is becoming positive, then it is stable, unstable region. And if always it is giving growth rate is negative, then it is stable region. And those things again we have plotted here in figure 3 and 4, how to find out the unstable region or stable region. So inside, if your parameter range or your system is such that your parameters are inside these bounded regions, so O, I, Ts, etc. If inside this bounded region you are considering your parameter range, then your system will be unstable. If you are considering parameter range outside this region, then your system will be stable. And these are known as actually stability boundaries. And to understand how it is happening, you can actually analyze the eigenfunctions, and you can do some energy budget analysis to identify the region of instability and stability. Okay, so again I am omitting this. So to understand the stability behavior or the source of energy, why that system is unstable, you have to study the energy budget analysis. You have to check that from which source which energy is coming. And once you know that, then you can explain easily. And to find out the source of energy from different places, you have to use your eigenfunctions of the system. Another thing, till now, whatever we have discussed, those are temporal stability analysis or spatial stability analysis. But one can do some other kind of stability analysis also, like absolute instability and convective instability. In the case of absolute instability, or your waves or perturbations are standing waves. They are not moving from one place to another place. In one place they are, and then it is either growing or decaying. In the case of convective instability, they are traveling waves. So in that case, waves can go along the axis, positive direction or negative direction. So such kind of instability one can also study. And that's all here from my side. So just I tried to give a quick overview of this kind of theory, stability theory in fluid mechanics, and where actually we are using linear algebra as well as dynamical system and numerical analysis. That overview I have given. So if you have any kind of question, I'll be happy to answer. So I'm stopping here. Okay, fine, fine. Yeah, thanks. Thank you so much.
Yes, sir. Thank you, sir. Am I clearly audible? Okay, sir. I'm just sharing my screen. Just a minute. Is my screen visible? Okay, okay. Thank you, sir. Okay. Honorable session chair and respected other participants. Very good evening to all of you. Myself, Dr. Surajit Chattopadhyay from the Department of Mathematics, Amity University, Kolkata. So I am going to deliver a talk entitled Theoretical Discussion on the Late Time Acceleration and Early Inflation of the Universe and Model Assessment through Information Theory. So at the outset, I express my sincere gratitude to Dr. Dash for giving me the opportunity to deliver this talk in this very nicely carried out FDP program. So it is clear from the title of the talk that this is centered around the accelerated expansion of the universe. Our universe is currently having an accelerated expansion phase. And it should be noted that this is not the only... It is in full screen, sir. So our universe is currently having an accelerated phase that is called the accelerated expansion. And this is, it should be noted that this is not the only accelerated phase of the universe. At the very beginning, according to Big Bang theory, immediately after the Big Bang, there was another highly accelerated phase that is called the inflationary expansion. So in my talk, I'll touch both. And furthermore, keeping in view the theme of this FDP, I'll have a discussion on the assessment of the cosmological model through probabilistic information theory, where I'll discuss how the entropy, Shannon entropy, which is a quantification of associated uncertainty, that Shannon entropy would evolve with the evolution of the universe according to our cosmological model. So I am going to the details of my talk. This is the brief plan of the talk. Firstly, I'll have a look into the evolution history of the universe, then an overview of late time acceleration, then an overview of Shannon entropy. That Shannon entropy is quantification of uncertainty. I have already mentioned that. I'll discuss this evolution of the entropy, that is the evolution of the associated uncertainty for the cosmological model. And finally, I'll discuss the reconstruction model, and that model assessment would be done through the probabilistic information theory. Now, according to Big Bang theory, our universe emerged from a singularity, which is a point of infinite density and gravity from where our universe began its journey. That initial singularity is a gravitational singularity. And as per the prediction of general theory of relativity that existed before Big Bang, and it is thought to have contained all the energy and space-time. And the CMB, that cosmic microwave background, I'm not going into the details of that. CMB is a very important part of cosmology. The cosmic microwave background is evidence. It is an evidence that the universe expanded from a very hot and dense state. And according to the Big Bang theory, the age of our universe is around 14 billion years. So that can be regarded as the age of the universe. Now, we have some alternate theories of the origin of the universe. Now, according to loop quantum gravity, there was a series of bounces that led to the origin of the universe. And the quantum fluctuations are responsible for the expansion of the universe. There is another theory, that is cyclic universe theory. According to that theory, our universe has resulted from ending up of an earlier universe, and from that our universe has started its journey. There is another suggestion, that is multiverse theory. That means according to this theory, there are many other universes like us. But in our talk, we will confine ourselves to the theory of Big Bang. That means we'll consider that the universe has started its journey from the Big Bang. Now this is cosmic wave.
Hello, sir.
Yes?
Sir, your slide is not moving, sir.
Slide is not moving?
Yes, sir.
Which can you see? This slide, can you see? There are some alternate.
First one slide, sir. Only.
Only the first one?
Yes, sir.
Just a moment. Just a moment. Can you see my slide now?
Yes, sir. Yes, sir.
Okay, so instead of full screen mode, I am keeping this. Okay. So can you see the picture of this cosmic wave? Anyone please confirm?
Yes, sir. Yes, sir.
Okay. This is the cosmic wave. So here it is an overview of the whole thing. Look at the beginning. At the beginning of the universe with Big Bang. And then what comes? Inflation. That is the initial condition for structure formation. As I've already told you, inflation. Immediately after the Big Bang, there was an immensely accelerated phase for a very, very tiny period of time, approximately for 10 to the power minus 32 seconds. And after that inflationary expansion, structure had formed and universe passed through various phases. And then it emerged, entered into the accelerated phase of the universe. And who is responsible for this acceleration? There, that concept of dark energy comes in. Who is responsible for the accelerated expansion of this universe? I'll come to that. And another part is dark matter. So there are two things, dark energy and dark matter. Now, dark energy accelerates the universe. That means it slows down the structure formation. And dark matter speeds up structure formation. And with this combination, the universe takes its own form. And finally, the present, which is dominated by dark energy. So this is an overview, a pictorial presentation of the evolution of the universe. And according to observations, the current universe is dark energy dominated. And 72% of the current universe is thought to be dominated by dark energy, and 23% dark matter, and 4.6% is other atoms. However, if you look at this circular part below this, you can see that earlier, that means at the beginning of the universe, it was dark matter dominated. 63% was dark matter. 10% were neutrinos, photons, atoms. But from this, we have evolved into dark energy dominated phase. Okay. So next we come to this slide. So as I am repeatedly uttering the term dark energy, what does it mean? Dark energy is considered to be responsible for the accelerated expansion of the universe. Exact nature of dark energy is not yet fully known. There are various models proposed in the literature for dark energy. I'll give an overview later. But before this, let us come to Einstein. In 1917, Einstein considered the cosmological constant. He added that cosmological constant to his field equations to obtain a static universe. Later, in 1931, all of us know that he removed the cosmological constant and he termed this as his blunder. Why he removed it? Because Friedman introduced cosmic expansion without the help of cosmological constant. And that is why Einstein abandoned that. In 1967, Zeldovich reintroduced the cosmological constant. So this cosmological constant has ups and downs. 1917, it was introduced. In 1931, it was abandoned. 1967, it was reintroduced, but it did not have much impact on cosmology after that. But in 1998, when the cosmology got a tremendous change due to the discovery of the late-time acceleration of the universe, as I have mentioned here, in 1998, based on 34 nearby and 16 distant type 1a supernovae, Riesettel first discovered the accelerated expansion of the universe. And soon after, almost at the same time, utilizing 18 low redshift and 42 high redshift supernovae, Perlmutter et al. Confirmed the discovery of cosmic acceleration. Both of them got the Nobel Prize in 2011 for the discovery of the accelerated expansion of the universe. That was a groundbreaking discovery in cosmology. And after that, there has been a resurgence of cosmological constant. Why? Because this cosmological constant, it is supported by observational studies, and it is thought to be the most fundamental form of dark energy, most fundamental candidate of dark energy. Here I have shown the press release of the Nobel Prize in Physics 2011. Here you can see, in 1998, cosmology was shaken at its foundations as two research teams presented their findings. Headed by Sir Perlmutter, one of the teams had set to work in 1988, and Bransmid headed another team, launched at the end of 1994, where Adam Rees was to play a crucial role. This was the press release of Nobel Prize Committee of 2011. Sir Perlmutter, Adam Rees, and Bransmid, they got the Nobel Prize for the discovery of late-time acceleration of the universe. And because of this late-time acceleration, we'll be having this dark energy, modified gravity, etc., which I'm coming in. Anyone please confirm, can you see this slide? Picture of two scientists?
Yes, sir.
Okay. So here, these are the pictures of Sir Perlmutter and Adam Rees. Perlmutter, his team, that study was published in Astrophysical Journal, and Rees et al., their study was published in Astronomical Journal, one in 1998 and the other in 1999. The interesting fact is that they were independently working on the decelerated expansion of the universe, because before their discovery, the universe was thought to have decelerated expansion. That means it is expanding with deceleration. That is why the deceleration term was very important. They were working on that. But surprisingly, the two independent teams found that the universe is expanding with acceleration. Now, to explain this acceleration, there are two approaches. One is dark energy, another is modified theory of gravity. Now here I have mentioned some very remarkable reviews on the accelerated expansion of the universe. One very fundamental review is Copeland, Sami, and Sujikawa, published in International Journal of Modern Physics D in 2006. It is a very highly cited and highly important review on dark energy. And later, there was another very nice book on dark energy by Amendola and Sujikawa. And there was another very nicely written review on dark energy was by Capozziolo, Nojiri, and Odintsov, published in Astrophysics and Space Science in 2012. This is the gravitational field equation. Here you can see G mu nu is equal to kappa square T mu nu. G mu nu is coming from gravity, T mu nu from matter. This G mu nu is called the Einstein tensor, T mu nu is the energy momentum tensor. Now, general relativistic approach that leads to dark energy, and another approach is modified theory of gravity. We'll be having a combination of these two. Now let us come to another aspect of this talk, that is the information theory, probabilistic information theory. Now, what is that? Here, this capital H, it is a Shannon entropy. As you can see, minus summation I is equal to 1 to n pi ln pi. This is this pi that comes from a probability distribution. And our target is to have an entropy maximizing probability distribution. We'll be doing this related to our cosmological model. Now, to maximize this entropy, we have some constraints. Obviously, probability greater than 0, greater than or equal to 0 for all I. Summation of all probabilities is 1. And all of us know that expectation of a random variable is defined as summation I is equal to 1 to n pi xi. So with all these constraints, we construct the Lagrangian. L is equal to minus summation I is equal to 1 to n pi ln pi minus alpha into summation I is equal to 1 to n pi minus 1 minus beta summation I is equal to 1 to n pi xi minus expectation of x. Here alpha and beta are the Lagrange multipliers, and we can have partial differential equations equated to 0. All of us know that. And finally, we can arrive at this equation. That is summation k is equal to 1 to n xk minus expectation of x into e to the power minus beta xk is equal to 0. So with this, we can have the entropy maximizing probabilities. Now if we can find a beta that is maximizing the entropy, then we can identify that is helping us to find the entropy maximizing probability distribution. Then we can have a model for which we can see how, with the change in the expectation, the associated uncertainty is evolving. If expectation changes for different sample sizes, then the associated uncertainty will also change. That we can see from here. We'll show this later. So before that, let us mention it. We'll be discussing two models of modified gravity in the light of dark energy. The advantage of modified theory of gravity is that here we, instead of confining to any specific model of dark energy, we can have explanation for the accelerated expansion. This FT gravity, it is also called teleparallel gravity. This is one very important component of modified theory of gravity. And these are some very important works on FT gravity. And another model of modified gravity that I'll discuss here is a chameleon Brans-Dicke cosmology. That was introduced by Joseph Bisber in their work published in Physical Review D. Here in this chameleon Brans-Dicke cosmology, this phi is the Brans-Dicke scalar field, and this is the Ricci scalar field, and capital R is the Ricci scalar field, and this is F phi into Lm is a matter Lagrangian density that is denoted by Lm and is coupled with phi via the function F phi. This function allows a non-minimal coupling between the matter system and the scalar field. So before going into that, let us have some overview on some phenomenological models of dark energy. I have already discussed about cosmological constant. That is considered to be the most fundamental candidate of dark energy. But apart from that, for the last couple of decades, many other models of dark energy have been proposed by several researchers. One kind of model is scalar field models like quintessence, phantom, quantum. These are direct generalization of cosmological constant. So these models are completely motivated by the Einstein's field theory. There is another model, Chaplygin gas model. This is a fluid description of dark energy. It is not motivated by field theory. However, it can be considered for unification of dark matter and dark energy. And another type is holographic dark energy model. It is inspired by the holographic principle. Here, dark energy density is proportional to the infrared cutoff. Some dark energy reviews. This first one by Varun Sahani in 2004. He is a great scientist of India. He is a scientist of Ayuka, Pune. He has some very nice works on dark energy. And Bamba, Capozziolo, Nojiri, and Odintsov that I have already mentioned. And Copeland, Sami, Sojikawa that I have already mentioned. So I am now going to the next slide. This is the FRW metric. To explain the late time acceleration of the universe, this is the FRW metric, Friedman-Robertson-Walker metric. Okay. These two are the Friedman's equations. Let us look at this. H is called the Hubble parameter. H is the A dot by A. A is the scale factor of the universe. For the current universe, it is considered to be 1. Okay. And this Hubble parameter is equal to 1/3 rho. 8 pi g, that can be regarded as unity. Now it is 1/3 rho. And 6 A double dot by A is equal to minus rho plus 3p. That can be with some rearrangement of terms that can be written in this way. Now here the question of dark energy comes in. Now if the universe accelerates, then A double dot has to be positive. Now if A double dot has to be positive, then rho plus 3p has to be negative. Now if rho plus 3p has to be negative, then that means what? P by rho has to be less than minus 1/3. P by rho is called the equation of state parameter. So for explaining the acceleration of the universe, equation of state parameter, which is usually denoted by W, has to be less than minus 1/3. That is the condition for the accelerated expansion of the universe. Without that, this acceleration is not possible, as it comes from Friedman's equation. Now we are going to our model, that is reconstruction model. Now our motivation is this work by Professor Varun Sahani and Alexis Starowinsky. Alexis Starowinsky is a great Russian scientist. He died in last December, in this December 2023. And Varun Sahani, a great scientist of India, reconstructing dark energy. Here, this gives us a motivation to reconstruct, to develop reconstruction models for late time acceleration of the universe. Reconstruction means here we are going to discuss how we can reconstruct a modified gravity model based on holographic dark energy. A holographic dark energy is based on holographic principle. What does this holographic principle say? According to the holographic principle, the entropy of a system scales not with its volume, but with its surface area. And in the cosmological context, this sets an upper bound on the entropy of the universe. And when it is applied to the dark energy issue, if we take the whole universe into account, then the vacuum energy related to this holographic principle is viewed as dark energy, usually called holographic dark energy. So what we are going to discuss is how we can consider the background evolution of the universe in the holographic form and in the framework of modified gravity, and accordingly how we can reconstruct a modified gravity model. These are some holographic dark energy models that has been proposed in the literature. Modified holographic dark energy, holographic Ricci dark energy, modified holographic Ricci dark energy, extended holographic Ricci dark energy, new holographic dark energy, and in very recent time after the COVID, there have been models of barrow holographic dark energy. That is not the purpose of this study. So let us look at this. Here we are going to discuss one reconstruction scheme of FT gravity that I have already told you, teleparallel gravity. For FT gravity, these are the modified Friedman's equation. I have already shown you the Friedman's equation. These are modified Friedman's equation. Here, this rho plus rho t. This rho t is the density contribution due to torsion, and Pt is the pressure contribution due to torsion. And holographic dark energy is chosen as rho lambda is equal to 3c square by Rh square. So this is our rho t and this is our Pt. Now, if we consider the holographic framework, then we can have this form rho lambda. That means we are connecting our holographic dark energy density with the density contribution due to torsion. That means we are considering that the density contribution due to torsion is coming from the holographic dark energy. That is, the background evolution of the universe is in the form of holographic dark energy. And scale factor is chosen in the power law form. And with that, we have the two solutions for Ft gravity. These are the two solutions. These two solutions are reconstructions. The first one is coming from the reconstruction with the first modified Friedman's equation. Second one is coming from the reconstruction from the second modified Friedman's equation. This is the second modified Friedman equation. This is the first modified Friedman equation. Okay. Now with this, we have reconstructed this. Here, we are trying to see how the model behaves with the evolution of the universe. We are observing that the reconstructed Ft is greater than or equal to 0. And here, for the second one also, for both the cases, this model is from the first Friedman equation, modified Friedman equation. Second one is the second modified Friedman equation. For both the cases, you observe that this Ft is staying at positive level. Here, we have observed a very important aspect of this. Okay, we have observed that they are staying at positive level. Now, are they stable against small gravitational perturbations? To see that, we have plotted the squared speed of sound, which is reconstructed p dot by reconstructed rho dot. This is the squared speed of sound. We are observing that in the first case, it is staying at positive level. However, in the second case, it is going to be negative. That means the second model is less feasible than the first one, because the first one is stable under small gravitational perturbations. And in this phase, let us have another reconstruction scheme where we will use another version of holographic dark energy, which is called the extended holographic dark energy. This is given by 3mp square. Mp is the reduced Planck mass, alpha h square plus beta h dot. H is the Hubble parameter, alpha and beta are the model parameters. This model is due to Granda and Oliveros. Their work published in Physics Letters B, they proposed this Granda or the holographic dark energy model with Granda-Oliveros cutoff. In this framework, we'll discuss chameleon branch decay cosmology. Here I have already shown that in the case of chameleon branch decay cosmology, there are two scalar fields. One is Ricci scalar field and the other is chameleon scalar field, and that is connected with the matter Lagrangian via a function f phi that I have already shown you. Here, this omega, this is the branch decay parameter. V is the potential, phi is the scalar field. These are the three modified field equations for chameleon branch decay cosmology. Now, when it is considered in the backdrop of extended holographic Ricci dark energy, we consider two cases. First, we consider the case where we have the potential and the function of phi all in the power law form. With these answers, we have this modified field, this result coming from the modified field equations. And we have this branch decay parameter for accelerated expansion. That means these two constraints are derived with the help of these answers. Now let us see how this model behaves. Let us see. This is a very important aspect of any model, that is the equation of state parameter model. So these constraints has been obtained, has been derived from this consideration of extended holographic Ricci dark energy in chameleon branch decay cosmology framework. And this is the evolution of the equation of state parameter with cosmic time t. What are you observing? This cosmic time t means the universe is evolving. And the equation of state parameter is coming from quintessence. That means this, what is quintessence? When equation of state parameter is above -1, it is called the quintessence. When it is below -1, it is called phantom. And if there is a model where there is a transition from quintessence to phantom, that is called a quantum model. Here we are seeing that there is a clear transition of the equation of state parameter from quintessence to phantom. So it's a quantum behavior as obtained by considering the extended holographic Ricci dark energy in the framework of chameleon branch decay cosmology. So this is a good finding where we can have a transition from quintessence to phantom with the acceleration of the universe. And this is a deceleration parameter. I have already told you. Earlier, the universe was believed to be decelerating. Expansion was believed to be decelerating. But with the discovery of accelerated expansion, this deceleration parameter has to be negative for the acceleration of accelerated expansion. Here, for this model, you are observing that there is a transition from positive Q to negative Q. Positive Q means deceleration. Negative Q means acceleration. During the matter domination, there was decelerated expansion. And during the dark energy domination, there is accelerated expansion. So here in this framework, we can have a clear view of transition from deceleration to acceleration. See, this transition is clearly shown here. Now, this is another case where we have made assumption about the scale factor and scalar field only. There is no assumption about the potential. So here we have a differential equation. And solution to this differential equation comes in as follows, which is the solution, the function of phi. That means function of the branch decay scalar field, f phi. Now, this is the reconstructed potential. Once we have reconstructed f phi, we can reconstruct the potential as well. I have already told you, we have not assumed anything about the potential or f phi. We have derived those. With this derivation, what we have obtained? We have obtained that this f phi is tending to 0 as phi is tending to 0. This is one condition for a realistic model. So this reconstruction generates a realistic model. Another one is that with the evolution of phi, v phi is increasing function of phi. So these two conditions support a realistic reconstruction scheme where we have reconstructed chameleon branch decay cosmology with the assumption that the background evolution is in the form of extended holographic Ricci dark energy. Now, if we consider higher derivatives of the Hubble parameter H in the framework of chameleon branch decay cosmology, then what happens? Here, we are showing just a few results just to show. Here, in the extended holographic Ricci dark energy, we have up to just H dot. If we have higher order derivatives of H, then also we can see that the equation of state parameters are around -1. That means they are consistent with the observations. So, irrespective of the order of the Hubble parameter, we observe that it is possible to have a reconstruction scheme of chameleon branch decay cosmology based on different versions of holographic dark energy. That is one great support for holographic dark energy towards reconstruction schemes of modified theories of gravity. This is called the RS trajectory. This is another important aspect that was introduced by Varun Shahani and his team. It is a very nice picture that shows how a dark energy model is deviated from the lambda CDM fixed point, that is the early universe. So here we observe that under this reconstruction, it is possible to reach the lambda CDM fixed point, that is R is equal to 1, S is equal to 0. So we observe that we can have unification of early inflation and late time acceleration through this reconstruction scheme. Now I am near the last phase of my talk. Now to assess the model through probabilistic information theory. To assess the model, what we do? We have SDSS-DR7 observational data of Hubble parameter as function of redshift Z. Okay. And based on the entropy maximizing principle, we have taken samples of different size. And with that, we have different values of the beta. That beta that comes from the Lagrangian that I have already shown you. And with that, the Shannon entropy is changing for our model. If we plot this, what you observe? We observe that this Shannon entropy is decreasing with redshift tending towards today's point. That means today's redshift is considered to be 0. So if Z tends to 0, Shannon entropy also is decaying. That means the uncertainty associated with the universe is decaying based on our model that we can observe through entropy maximization principle. This approach is completely new in the area of cosmology. This in this work, this is published in Physica Scripta. This was done by me and my PhD scholar Shanghati Saha. Here we can see how with the evolution of the universe, the uncertainty decreases. That means the current universe has less uncertainty than the early universe. So what is the fate of the universe? That is a great area of study. What will happen in the very later stage of the universe? What will happen in the future? We are working on that. How this uncertainty evolves toward the future. How our models shows the future of the universe. How this will the universe end up? Or will the universe evolve to a new universe? Those are matters of study. And with that, I close my talk. And thank you for your patient hearing. Thank you. Thank you, sir.
Sir, please slide number 19 and 20.
Okay. Thank you, sir. So, should I close it?
Hello, sir. Am I audible?
Yes.
I have one question from slide number 19. Can you open, please, the slide number 19 and 20?
Just a minute. Slide number 19. Yes, sir. I have to share again. Just a minute. Yes, sir. This is slide number 9.
So you have constructed this graphs in 3D.
Sir, I can't hear you properly, sir. Can you be a bit louder?
Yeah. You have constructed the graph in 3D. So my question is that how have you constructed this graph using just
how I constructed the graph? Is that your question?
Yeah, using Microsoft.
This is done in Mathematica.
Mathematica, okay.
Mathematica 3D plot.
Is there any solution to construct this graph? Or,
this is a 3D plot. Here, our target was to see how this is the cosmic time t, and this is another model parameter. How with the evolution of these two, we can see the evolution of ft. That is why we did this 3-dimensional plot. This is done in Mathematica.
Okay, sir. Thank you. Okay, thank you, sir. My question is.
Good evening, sir.
Yes, sir.
Thank you for your nice presentation.
Thank you, sir.
Sir, can you suggest some book or can you show your references?
There is a very nice book. There is a very nice book by, as I have already shown you, by Amendola. Luca and Amendola, that book on dark energy. That is a very nice book. Very nice, excellent book. That is a book by Cambridge University Press. Luca and Amendola. And there is another very nice review. You can it is openly available on archive. That is the dark energy, dynamics of dark energy, published by Copeland, Sami and Sujikawa. It was published in International Journal of Modern Physics D. You can study it. It is like a book. If you print out it is like a book. It is excellent review of dark energy. Very nice review. Anyone can study that.
Sir, could you please suggest some topics related to celestial mechanics and chaos theory in the combination?
I couldn't hear your question exactly. Can you please repeat?
Yes, sure, sir. I actually want to ask some new ideas or topics for my research in the domain of celestial mechanics and chaos theory. I mean, intersection of celestial mechanics and chaos theory.
Okay.
If you could.
What is your question?
My question is to want the new topic for doing work.
You want new topic for celestial mechanics and chaos theory?
Yeah, in the intersection of celestial mechanics and chaos theory. I mean,
yes, of course. Here, there is an immense scope. As so far I have explored the area of you can quantify the uncertainty associated with any model. If you have some observational data, you can validate any model with the observational data. Usually, what people do is there is a reduced chi-square method for fitting observation to fitting model to data, reduced chi-square. But here we have, with reference to your question, here instead of doing that, what we have tried is we have tried to explore the uncertainty associated with the system. Here, this model is a cosmological model. So here, your topic obviously is a very nice question. Your topic obviously can be any model, any celestial model, where you can explore the associated uncertainty through the Shannon entropy, through the entropy maximization principle. That you can explore, because that is a very less explored area. In other areas, this has been done, but in cosmology or astrophysics, this is a very less explored area.
Sir, could you please write the topic in the chat box?
In the chat box? My net connectivity is a bit slow. Another option is that I can send it to Professor Das. You can share it from him. Because here in the chat, my net connectivity is just a moment. Sure. I'm opening the chat box. Yes, I am writing. I'm writing. Yes, I have posted my answer.
Thank you so much, sir. Your presentation was really very nice. And
Thank you. Thank you. Okay, sir. So should I close it? Okay.
Uh, am I audible? Okay. Shall I start? Okay. So, very warm welcome to all of you. Good evening, everyone. First of all, I would like to thank the organizers for giving me this opportunity to interact with you all. And today I'll be speaking on one of the mathematical models that we had worked on, and that is about the transmission dynamics of chikungunya virus, right? So how this infection, how does it my screen? I hope you all are able to see my screen. Okay. Okay, so as sir has already told you, my affiliation is Sri Guru Tegh Bahadur Khalsa College from DU. Okay, so we'll be speaking on this transmission dynamics of chikungunya infection. So see here, in my talk, I'll be giving you a brief overview of the biological aspect of this infection, because first of all, we need to know the biology behind any infection. Then only we would be able to formulate the mathematical model for that. So then I will come to the basic mathematical models that we commonly use in epidemiology. Now here, probably as you people are already into this workshop, which is, giving you so much exposure to mathematical models. So probably many of you might be familiar with these models, but I'll be just giving you a quick go on that. And then we'll be talking about our model, the formulation and what does it signify, and then the stability analysis and the numerical simulation. Now, talking about chikungunya infection, it's a vector-borne disease. It is, it gets spread to the human population by, actually, it would be getting introduced to the human population by a vector, which is a mosquito, right? And once it enters the human population, now from human to human, again, it needs a carrier. So that carrier is again the insect, the mosquito. So now, going to the history of this, it actually started as an epidemic in these Comoros Islands, And then this is about the brief history. It was for the very first time, it was observed in 1952, right? And then, hello, yes. Shall I continue? Okay. So it started in 1952, and thereon in Bangkok, it was observed in 1958, then in Indian states in 1960s, and then from there on, it is being observed as an infection off and on, right? So now, when we come to the basics of this infection, as I already told you, it's a vector-borne viral disease. So vector is going to, by that mosquito bite, the virus would be injected into our bodies. And the mosquito, which is the carrier here, is the Aedes aegypti mosquito, right? And once this infection is transmitted into our bodies, then the common symptoms that we feel are high fever, joint pains, and then nausea, headaches, rashes, and all these. Right now, the main thing here is, viral fevers and the viral, other than COVID, the usual viral infections we used to observe, they, just for a period of say 4 to 5 days, the symptoms would be prominent, and after that, the recovery period would start. But it was actually observed in chikungunya infection that there used to be a very long phase till the infected or individual would gain the complete recovery. So here, this period is actually very important, and this is what we targeted in our model. See, I have given a brief, difference between chikungunya and the dengue. Both are transmitted through a mosquito, but in chikungunya, we had already seen that there's an extremely long recuperation phase. And what do we mean by a recuperation phase? It's actually the phase during which the immediate or the most acute symptoms, they'll get subsided, but still there will be symptoms and uneasiness that the patient would be experiencing, and therefore he cannot be called completely recovered. So here, the symptoms like joint pains, rashes, these are going to continue for a long time, these headaches and all. And this was observed very commonly in chikungunya, that even, for a period of more than a year, the patient used to complain about the joint pains. So the immediate and the, acute symptoms, they used to get subsided in a period of say 1 week or at the most 10 days. But then these kind of symptoms, they used to linger on for a period of year, and in some cases even more than a year. So this was a very important and a very different kind of, observation in the case of this chikungunya infection. And this period, this is actually the biological term for this is recuperation phase, and this could go over a year, as we have already discussed. So what we did was, I'll just come back to this slide once again. We actually targeted this recuperation phase, that the model, if we are forming any model for chikungunya infection, then the recuperation phase should also be observed, and the analysis of the model and the transmission dynamics of the disease, that should involve this recuperation phase as well. So now I'll be coming to my model, but before that, I'll be speaking on some basic models, and I hope many of you might be knowing about this. See, the whole human population, commonly if you see the major divisions that are done for human population they are divided into, first of all, susceptible humans. And susceptible humans means they are the humans or the population part that is prone to get disease, prone to get infected. Then once it gets infected, then there is an incubation period of this infection, when the virus that has entered your body, it will get multiplied, and the symptoms would not be that clear during this phase because the infection is being built up. But once it is completely built up in your body and the symptoms, they become prominent, then we talk of this infected phase, right? And then of course, after a period of whatever the disease you're going through, after a period of time there'll be recovery. So that is the recovered compartment. So what is this? This is actually the basic compartmental diagram for the human population, getting divided into these 4 basic components. So now this is just one visual representation of that, and the other models are, in many models you can see they are not ring the E part, the exposed part, and they are simply talking of SIR, right? Then there might be diseases where after recovery again there's a chance of getting the SEIRS models and so on, right? Now, when we talk of any disease which is vector borne, then what we need to do here is we need to study the dynamics of the vector population as well. So when we talk of SIR-SI, that means we are talking of SIR part of the human population. The human population is divided into 3 compartments here, and the vector population is divided into 2 compartments, the susceptible and the infected population of mosquitoes or any vector that is acting as a carrier to inject the infection into the human population. So these are, again, there are many more type of models available in literature, so I've just cited some basic ones here. Now when we come to the compartmental diagram, where we can see the interaction between the human population and the mosquito population, then you can just see to this again, as we had already seen. This is SEIR population compartmental diagram for the human population. And then below is the SEI compartmental division for the mosquito population. Right. Now, this is again based on the biology. We say that once a mosquito who has caught infection, now how is mosquito going to get infection? It's like if the mosquito bites an infected individual, then the blood that it sucks from the infected individual, that will make this mosquito infected. So again, there is going to be some incubation period for the mosquito as well. So after susceptible, there is going to be the exposed phase, right? And after that, the symptoms, you can say that the symptoms, they'll become acute, and the population would be then, the dynamics will take it to the infected compartment. But in humans, as we see that after some treatment or after a phase, a period of say a week or so, the individuals, they'll get recovered. But in mosquitoes, it's not like that. Once the mosquito has got the infection, then ultimate thing is, now after getting the infection, there is some fixed period that up to that period it can survive, and after that the mosquito will die. So we don't consider the R compartment in the mosquito population. Right. Now, this is our model. What we had done here is, we considered for the chikungunya dynamics, we considered SEI and this R. This we had already seen that SEIR human population is divided into 4 compartments. We have already discussed that. What different we tried to do here is, we introduced another compartment that we denoted by R prime, and this was the recuperated phase. So again, the mosquito, mosquitoes also I'll discuss once. We have divided the mosquitoes into 3 populations, X, Y, Z. Now X was the susceptible part of the mosquito population. Then Y was the exposed part of the mosquito population, and Z was again the infected part. Right. So once there is an interaction between some infected mosquito and a susceptible human being, so the infection from the infected mosquito, it will get transferred to the susceptible human here. So this arrow actually indicates that this mosquito in the Z compartment is going to, give infection to the human in the S compartment. And similarly, the mosquito that is susceptible to get the infection. It can get the infection from the infected human. So it will be getting infection from this eye compartment. So humans in the eye compartment, they'll be giving infection to the mosquitoes in the X compartment. So this is like two-way interaction. How humans are going to get the infection from the mosquitoes. These are the two compartments that are going to interact. And again, these two compartments, they are going to interact, and then the mosquitoes are going to get the infection. So now, again, wherever there is a dynamics, there has to be some rate of flow. What is the rate with which the susceptible individuals, they are getting converted into the exposed individuals. So there are going to be some rates for that. We have just indicated those rates by these Greek letters, and I'll be giving you the description of what these Greek letters, they are actually signifying. Now look here, we have this SEI prime R. These, as we have already seen, these are the human populations, and XYZ are the mosquito populations. So these we have already described. These R prime are the humans in recuperation phase, and these are the human population that have recovered fully. And then these are the mosquito population division. Now the rates that we have used here is like there is going to be some natural birth rate for humans. So that is taken as mu, then this is beta. And if we go back to this beta is what? It is the mosquito biting rate for transfer of infection from infectious mosquito to the susceptible human. So there has to be some rate at which rate the mosquitoes, they are biting the humans. So that has been taken by beta, and then again the progression rate from exposed to infected. So if we go back to our model, you can see that from Z to S, the infection is going to get transferred by some rate, which would be beta BH. Again, we have described that thing completely in the paper also. And that all depends on how frequently these mosquitoes, they are biting the human beings. So this beta, as we have seen, that is the mosquito biting rate. So depending on what all factors do you consider in your model, these rates, they are going to change accordingly, right? So this is the description of all this, as alpha is what? From exposed to infected individual. So if we go from exposed to infected individual, this rate of transfer from this compartment to this compartment, we have taken it as alpha, right? So similarly, all other rates, they have their own meaning, and then they are all being described here. So I'm not going to talk about each and every rate, because I have given all this, and if you want, I can share it with you as well. Now we come to the model. What was that complete thing? From when we talk of the population in the S compartment, then since these individuals in the S compartment, they are going to get infection from the mosquitoes in the Z compartment. So there has to be some interaction between this Z and S. And that this NH, what is this NH? NH is actually the total population. So complete description, as I told you, this is, each model is going to have a number of rates, and the complete description, that is all, altogether a very lengthy kind of thing. So I've not written everything here, but NH, as we have used in the paper, is the total human population. So this is like out of this total human population, ZS, this is going to be that fraction which is going to interact, and then accordingly this term has been formulated. So now what is going to be the rate of change of susceptible human population with respect to time? So this is mathematically being described by this equation. So likewise, this is the rate of change of exposed population. Now as we can see, the exposed population, from exposed compartment, the individuals are going to move to the infected compartment. So there is going to be some part of E which is going to leave this compartment, and that part is going to go into the infected compartment. compartment. So as we know that inflow and outflow rule for mathematical models. So you can see that here minus alpha E, that is leaving out from here, and it is going to enter into the next compartment, which is being represented by I. Similarly, this part was leaving, this part of population would leave from here and would enter here. Right. So likewise, this complete thing has been formulated. And then the main focus was on this equation because we were, trying to explore something on the recuperated individuals. So dr prime by dt, this is this part. Again, the infected population from here, when it leaves, it enters the recuperated phase. And the recuperated phase, the part that leaves from here, that means the person's recuperation phase is now over. So that person would now be transferred to the recovered compartment. So this part, when it leaves from here, it is going to enter into the next compartment. So that was it. So we can have, as much discussion on the model as you want, but due to the time constraint, I have just highlighted a few things about the model, and same way we can follow the other equations also. For the equations on x, y, z, these are three equations which are representing the rate of change of mosquito population, the rate of change of susceptible mosquito population, then the exposed mosquito population, and the infected mosquito population. Right. Now, again, what we do here is we will be talking of now the stability analysis of the model. So what is this? This is formulation of that model. And now we want to talk of the stability analysis of the model. So for the stability analysis, we need to talk of both types of equilibriums. So first, this is the disease-free equilibrium. This disease-free equilibrium has been evaluated using the model, and I hope majority of you might be knowing this, that when we want to find the disease-free equilibrium, we have to keep in mind that the population is free from disease. So wherever we have disease, like E compartment is a compartment which is going to possess the disease. But since the population is disease-free, that means this E part should have the value as 0. I should have the value as 0. So we use I equal to 0, E equal to 0 everywhere in the complete model. This R prime is still having infection, right? So again, that will be taken as 0 if we are talking of the disease-free equilibrium. And we put 0 for all this, and we solve this simultaneous system of equations keeping this in mind. And then we get this complete thing. This is the disease-free equilibrium. Then I have just given this reproduction number, the expression that we got for the reproduction number, but then there's a complete mechanism behind this. How do we do that? We, we have used the next generation matrix approach, right? So what we do here is like the literal meaning for the reproduction number is if, one infected individual, if it is introduced into a completely susceptible population, then from that one infected individual, how many individuals are going to get the infection? So in other words, we can say that it is the expected number of secondary cases which would be produced by a single typical infection, which is completely disease-free. So we assume that the population is not having any infection, and then somehow one infected individual enters the population, and then through that one infected individual, how many more individuals they can get infected. So based on the model, the rates that you have used in the model, and using the next generation matrix approach, we then find this reproduction number. And that's a clear-cut methodology for every model. We do that. So this is the reproduction number that we got for our model. Then this is the endemic equilibrium point, right? Now the other one was the disease-free equilibrium point, where we assume that the disease is not there in the population. But when we talk of endemic equilibrium point, so this is, that equilibrium point where we assume that the disease is very well persisting in the population. So for that, what we do is the basic, again, methodology is just solve this complete simultaneous system of differential equations. We have to solve this system. And since for the disease equilibrium point, you had used E, I, R prime as 0. Right. So it came out to be a very simplified thing. This was the disease-free equilibrium. But when you compare it with the endemic equilibrium, now you will be solving each and every equation completely. So this is the complete endemic equilibrium point. So it looks like, very tedious kind of expressions are here, but that is all due to this, because now here none of the infected, component, you're going to take it as 0, and that is going to have some value in terms of the rates that you are using. Now, again, one more thing is, when we talk of endemic equilibrium, so that means we are assuming that the, population is having infection. So the reproduction number, in that case, it has to be strictly greater than 1. Because how is disease going to persist in the population when the infected individual, one infected individual, that is going to spread infection to more individuals. So if R naught is less than 1, in that case, the interpretation for that would be diseases, eventually it is going to die out, because R naught is less than 1. That means not even one complete individual is going to get infection from that infected individual. But when there is, disease in the population, that means R naught is greater than 1. So every infected individual is going to transmit the infection to more than one susceptible individual. So in that case, we take R naught as greater than 1. Right. Now, these were the stability results. And when we, there are complete proofs. I'll be showing you the paper as well. There are complete proofs for that, and different strategies that are used in stability analysis. We have, followed all those proofs, and finally the results that we got were the disease-free equilibrium. When the analysis for disease-free equilibrium was done, it was found to be stable. But again, when R naught is less than 1, because it is disease-free, so in that case, the stability would be attained for R naught less than 1. But if R naught is greater than 1, then it would become unstable, right? So this is very logical, and we can relate it to the basic mechanism of any disease, that is, and then endemic equilibrium, if we say so, then in that case, the stability and even the existence, that would depend on this factor, whether your R naught, whether the reproduction number is greater than 1 or not. It has to be greater than 1 so that the endemic equilibrium exists. Endemic equilibrium exists means the disease is there in the population. Right. Now let us come to some simulation part. What we did here was, we tried to see the dynamics of the infected individual for the case when R naught is less than 1. Now, what do we mean by R naught less than 1? As we had discussed just now, R naught less than 1 means the, disease is going to die out. Because, see, initially what you can see here is we started with 500. We started with 1,000 infected individuals in the population, then 1,500, 2,000, 2,500. So in any population, if there are 500 infected individuals, then since R naught is less than 1, that means actually disease is eventually going to die out. When one individual is not going to spread infection to even one more individual, because R naught less than 1 means it can be any value less than 1, so half, 1/4, whatever. So one infected individual can spread infection to just 1/4 of the individual, right? So that doesn't make sense. So eventually, what is it? 500 individuals for a period of time, okay, the infection is going to rise up. But since R naught is less than 1, so eventually this infection has to die out. So the same dynamics you can say for, you can see for any kind of initial population of infectives that you take here. So this was the observation for the infected individuals and their rate of change with respect to time when R0 was taken less than 1. Right. And now it is for R0 greater than 1. So when R0 is greater than 1, see, if you see this, finally, this graph, it is touching the x-axis. That means the infected individuals, they are coming to 0. It is touching the x-axis. So ultimately, the infected individuals, their number would become 0. That means disease is going to die out. But here what you can see is since R0 is greater than 1, so this is not going to die out. It is being continued in the population. So over a period of time, it is getting decreased, but still it is there because R0, the values of R0 that we had taken, they are not values greater than 1. That means the rates that we had selected, they were in such a combination that the value of R0 came out to be greater than 1. So that is the comparative graph for the infected individuals for both the cases when R0 is less than 1 and greater than 1. So, okay, the same graph here, you can see both the graphs side by side, right? Here, at 90, you can see it has touched, and in fact, before 90, it has touched, but here, even after 100, it is not going to touch the x-axis. Right. So because of the basic difference that here the scenario is that the population is going to have infection. So that is being clearly seen in the graphs as well. Right. Now, let's come to this recuperated humans. The humans who are in the recuperated phase, when R0 is less than 1, ultimately, they are also going to get this sorry, I'm so sorry, they are also going to get reduced to 0. So because R0 is less than 1, right, so ultimately the spread of infection is coming to an end. So the population which was in recuperated phase, after a period of time, it has to come to 0. And since the R0 is less than 1, so no more infected individuals, they are getting added up into the population. So ultimately, no more entries into the recuperated phase, and the entries who were already there in the recuperated phase, finally, after a period of time, they gain recovery, and then they are actually touching the x-axis due to that only. And here, when R0 is greater than 1, again, you can see this difference. For R0 greater than 1, it is not touching the x-axis. So over the same time period, it was the earlier graph, touching the x-axis, and here after, again, before 90 even, it has touched x-axis, and here it has not, because again, since the basic difference was, this is the case where R0 is greater than 1, right? Now see, what is this? We have here compared the infected individuals with the recuperated individuals in the same time frame. So what we do here is, infected individuals, you can see this is being represented by the pink graph. So infected individuals, they are going to come to 0 at a very faster rate as compared to this green graph, right? Here you can see the peak is not that high, because this infected phase in chikungunya, it is not infected phase is not for a long period, because what we are taking in infected phase is the acute symptoms. They are not for a long period, or at least not that long period as compared to the phase which is there in the recuperation phase. So recuperated phase, that is going to be the individuals in the recuperated phase, they are going to stay for a longer period. They are going to stay until and unless they have gained complete recovery. So the people in the recuperated phase, they are always going to be more in number as compared to the individuals in the infected phase. So this actually shows the comparison between the two, right? And then this is again for R0 greater than 1. And this graph was for R0 less than 1. So ultimately, due to this, this is definitely going to stay for a longer period. much longer period as compared to this infected population, but ultimately they both have to come to an end because the cases R naught is less than 1. But when you take it for R naught greater than 1, then the nature is still the same. The infected humans graph, that is going to lie far below the graph which is actually representing the recuperated humans. But since it is the case when R naught is greater than 1, so therefore what we have here is this is not going to meet the x-axis. That means this is not going to come to an end. Why? Because R naught is greater than 1, so disease is going to it will be continuing in the population. So again, that is showing you the difference here, right? And now these are few references that we had used. And this book I have highlighted. This is actually one of the basic books on introduction to mathematical epidemiology. So if you are any one of you is interested in this, so just a basic course of epidemiology is following the thing, how the epidemiology models, how are they formulated, how are they worked on, what is the stability, and so many other aspects associated to that. I would recommend this book as a very good book to start with. And then these are again some of the references. Here we have a reference. This reference number 10 is also very important because this talks of the mechanism, the methodology, how reproduction number is calculated. So the next generation matrix approach that I had been speaking of, that is through this paper. That's a very basic and fundamental and the most popular paper that everyone would be using, whoever is working with the reproduction number thing. So that's all. And now I would be, happy to answer any questions. If there are any questions for me.
Ma'am?
Yeah.
Ma'am, in the graph, there are 4 different colors are showing the previous graph results.
Okay, yeah.
What does mean of these 4, 5 different results?
Okay. No, these are not 4 or 5 different results. Actually, we had, tried seeing the dynamics taking different initial values. What we do here is we say that if the, let us assume that at t equal to 0, at, this is t equal to 0. At t equal to 0, let us assume that the recuperated individuals in our population were 1,000. Then what is going to be the nature of this recuperated individuals over a period of say 90 days? How they are going to, what kind of pattern their graph is going to show? That means what is the dynamics of this population? But there we observe this blue graph. But then we changed the situation. We said that, okay, let us say if initially the population had been 2,000, then what would happen? Then you get a graph, this brown one. So they are all the graphs representing the recuperated humans only. But with different initial values, we had done that just to see how they are going to behave. So they are going to behave in the exact similar form. The nature is going to be similar. They are going to have a peak and then there will be a downfall. And eventually, since it is R naught greater than 1, so it will not meet the x-axis, right? That is not different. These are not different graphs. They are the graphs of the same compartment, but with different initial populations for the same variable. Right? Is it clear?
Yeah, ma'am. And one more question, ma'am. How do we calculate this R0?
Okay. See, that's okay. If you give me a minute, can I show my paper here?
Yeah, sure, ma'am.
Okay. See, I would like to share my screen again. Are you able to see this research article on your screens?
Yeah.
Okay. So now in this paper, I'll just come to that point which you are interested in. This is the model formulation. I had given you the model there. And now here we have, given the complete explanation of each and every equation. How do we get it? So this is the formulation of the model, and then the complete compilation of all the equations that gives us this model that I have shown you in those slides, right? This is the compartmental diagram we have talked of. These are the tables that we have seen here. And now see, these are the values that we have taken from, literature, literary sources, and a few values we have observed on the basis of the data available, right? Now, these are also the values. Now, taking this set of values, the value for R naught obtained was less than 1. And taking this set of values, the value of R naught, it came out to be greater than 1, right? And if you just want to see how do we calculate R naught, that was the numerical part that we have seen. And now I come to this. This is the next generation matrix approach. Now here what we do, we have to form two matrices. This is one matrix F, and then this is matrix V. What we do is we actually divide our complete mathematical model into two parts. We separate the infected part, and the variables which are not having the infection, they are separated into two parts. So this is, now you need to know a little theory behind this, then you would be able to form these two matrices. Once we form these two matrices, this is the actual basis to come to the reproduction number. Then what we do is we form the corresponding matrices. You can see this is some italicized matrix F, and this is an italicized V. Now we form this F and V. These are the matrices which are obtained from these matrices by taking the Jacobians of these two matrices. So we find the Jacobian of this matrix, we'll be getting this F. We'll be forming the Jacobian of this, and we'll be getting V. Then what we do is we take FV inverse. We take the product of these two matrices and we multiply them, and we get a resulting matrix denoted by G. Okay, now G is a matrix, and what we do for the reproduction number, we have to pick the largest eigenvalue of this matrix G. So when you take the Jacobian of these, and Jacobian has to be taken in terms of variables here. First equation was SI, SEI, whatever. The variables that are corresponding to these equations, the Jacobian has to be taken by using the partial derivatives with respect to this. And once you form the Jacobians, you get two matrices, multiply those two matrices, and the resulting matrix is going to be a matrix of higher dimension, and then take the eigenvalue. So what is like here, you can make use of softwares also done. Major part we had done on Mathematica, right? So this is the reproduction number that we get here.
It's showing that eigenvalue is one of the reproduction numbers. So there will be more eigenvalues. So which eigenvalue you have to consider?
You have to pick the largest eigenvalue. See, this is what I'm saying. When you go to this, these two references, the other reference that I, highlighted in my presentation also, there's a reference that actually, has been the main foundation of evaluation of reproduction number. So just go through that reference. That is going to help you a lot, and you will be getting the complete command of the methodology to calculate the reproduction number. You will be getting eigenvalues, the complete matrix that you get after taking this product. That is going to be a square matrix, and that square matrix, the dimension of that square matrix, if it is 6 cross 6, so you will be getting 6 eigenvalues, but you have to pick the largest one. The largest one would be the reproduction number. So that's a complete, as I told you, it's like an algorithm for you to follow. So that's a standard methodology, and based on that you reach here. taking this as the reproduction number. Is that fine?
Okay, so this formula we have generated by the softwares?
Yeah. A part of it probably you might be able to do manually also. That depends on what is actually the dimension of your model. The more number of variables, the Jacobian and all, that will be the matrix would be a matrix of higher dimension and would be difficult to handle. So in that case, partially sometimes we do it manually, and at some points we need to work on softwares, and sometimes softwares, they might not be giving us the answer in the desired form. Then we take the expressions from there and then try to sort it out manually so that we can get a desirable form. So that is all, that depends on, if you have a smaller dimension model, then definitely you can do it manually also. But here I have used Mathematica because at many points we felt like get the expressions, so that you need.
Okay, thank you, ma'am.
Okay. Yes. Any other question? Okay, okay, sir. Thank you so much. Thank you. Thank you so much. Okay.